Geological catastrophes are destructive events that, in the scale of Earth's time, are merely brief moments, but their consequences can alter the planet's appearance for millions of years. Earth, as a living organism, experiences cycles of creation and destruction, where each catastrophe serves as a catalyst for new geological processes. For instance, tectonic movements, which cause earthquakes, occur due to the slow, almost imperceptible movement of lithospheric plates, shifting at a speed of several centimeters per year. These movements can lead to the formation of mountain ranges or deep depressions, altering landscapes and creating new ecosystems. Volcanic eruptions, originating from Earth's interior, expel tons of magma and ash, which, upon cooling, form new lands. For example, volcanic activity on the Hawaiian Islands has created an archipelago that continues to grow due to constant eruptions. These processes occur amidst the grandeur of Earth's tranquility, which cannot be disrupted even by the most powerful catastrophes. Time in geological terms flows slowly, and even the most destructive events are perceived as part of the natural cycle. Periods of calm between catastrophes can last for millions of years, allowing life to develop and evolve on the planet. During this time, soils are formed, flora and fauna develop, and unique ecosystems are created, which in the end are subject to the same catastrophes that created them. Scientific research shows that each geological catastrophe, whether it is a meteorite impact or a mass extinction of species, opens new opportunities for adaptation and evolution of existing organisms. For example, after a catastrophe that occurred 85 million years ago when an asteroid struck Earth, the dinosaurs went extinct. But this allowed mammals to occupy the vacant niches and ultimately led to the emergence of humans. Geological catastrophes not only destroy but also create. They form new continents, change ocean currents, and influence the climate. In this sense, Earth is an endless cycle of destruction and creation, where each event, whether catastrophic or constructive, plays its role in the planet's history. Ultimately, when we look at the scales of time, it becomes clear that catastrophes are merely moments in Earth's multi-billion-year history, which, nevertheless, leave a deep mark on its landscapes and ecosystems. For example, scientists believe that in the last 500 million years, there have been at least 5 mass extinctions, each of which has fundamentally changed the appearance of life on the planet. These events serve as a reminder that even the most destructive catastrophes can create conditions for a new beginning. The evolution of life on Earth is inseparably linked to these catastrophes, and each new generation of organisms adapts to changing conditions, thereby creating the richness and diversity that we observe today. Earth, despite all its catastrophes, continues to live and change, and each destructive event becomes part of its endless history, in which catastrophes and the creation of new forms of life intertwine in a complex dance. Scientific data show that tectonic plates move in conjunction with internal processes such as mantle convection, and as a result, even the most powerful geological catastrophes ultimately contribute to the formation of new structures and forms of life. For example, the last time significant tectonic activity occurred, new mountain ranges were formed, which are now home to unique flora and fauna that are not found anywhere else. According to astronomers' data, Earth formed approximately 460 million years ago from a protoplanetary gas dust cloud composed of hydrogen, helium, and heavy elements ejected by stars during their deaths. Initially, this cloud was cold and sparse, but under the influence of gravity, particles began to gradually attract each other, forming more massive clumps of matter. Imagine this primordial chaos. Particles colliding in the vast cosmos create an incredible noise and heat. Energy from these collisions heats the matter to thousands of degrees. And during the process of coalescence, protoplanets form, which in turn become more massive, attracting other materials to themselves. About 14 million years after the start of this process, a portion of the matter formed into a glowing sphere that became the basis of our planet. The temperature on Earth's surface at this time reached thousands of degrees, and the atmosphere was filled with acid vapors and water vapor. Constant collisions with other celestial bodies, such as asteroids and comets, added mass and energy, as well as created craters that later became a characteristic feature of the landscape. One such collision, the size of Mars, known as Theia, led to the formation of the Moon and was so powerful that it ejected a massive amount of material into space, which later became Earth's satellite. The process of Earth's formation was not only hot, but also dramatic, accompanied by explosions and bright light effects. The protoplanet, in essence, was a giant volcano, spewing magma that gradually cooled and formed the crust. This crust, in essence, can be considered the first shell of our planet, which later became the basis for the formation of continents. While millions of years passed, the surface of Earth continued to change, forming new structures and creating conditions for the emergence of life. Gradually, as the temperature decreased, oceans formed. Water, condensing on the surface, created conditions favorable for the formation of the first organic compounds. This transition from a glowing sphere to a more stable planet was slow and difficult, but it laid the foundation for the further development of life on Earth. The primordial chaos and unimaginable heat began a long path that ultimately led to the appearance of life as we know it. Over billions of years, the planet has evolved from a glowing object to a place where a complex ecosystem with unique forms of life emerged. Parameters such as temperature and atmospheric composition changed under the influence of volcanic activity and comet impacts, creating conditions for further development. The formation of Earth's primary crust began approximately 800 million years after its formation, as the molten surface gradually began to cool. Temperatures exceeding thousands of degrees Celsius gradually decreased, resulting in the formation of a thin, solid shell that served as the foundation for future continents. This process was extremely unstable. Internal planetary forces, such as volcanic activity and tectonic movements, constantly tore apart the new crust, creating fractures and faults. The mantle beneath the crust continued to emit heat, contributing to the formation of volcanoes that ejected molten rock onto the surface. Around 30 million years after the crust began to cool, the first continents emerged. These continents were fragile, like glass, and constantly subjected to external factors such as meteorite showers. Each meteorite impact left craters on the surface, which were subsequently filled with water, forming primitive oceans. Meanwhile, water vapor and carbon dioxide began to accumulate in the atmosphere, further promoting cooling. During this period, small land masses began to form on Earth's surface, surrounded by volcanic activity, creating hazardous conditions for life. Eventually, the surface became cold enough to no longer glow with molten light, plunging into darkness. This was the time when Earth finally achieved its first tranquility. But its fragile crust remained under constant pressure from internal forces, ready to be torn apart again. At this stage, the evolution of chemical elements began, contributing to the formation of the first simplest forms of life. The primary crust we are discussing was not just a layer of solid Earth, but a dynamic structure capable of changing under various factors. For instance, during the formation of the crust, rocks such as granite and basalt were formed, which became the primary building blocks of future continents. These rocks formed as a result of the crystallization of molten minerals, occurring at depths of up to 30 kilometers. Simultaneously, due to the constant movement of plates, Earth's crust was subjected to deformations, creating mountain ranges such as the Himalayas, which continue to grow to this day. Over time, this complex process allowed the planet to take on the shape we know today, becoming a home to numerous ecosystems and living organisms. Approximately 4.5 billion years ago, Proto-Earth, not yet having reached its final form, began to approach the planet Theia, which was about the size of Mars. These two celestial bodies, moving in orbits, intersected in a slow, almost dance-like process that lasted for millions of years. During the approach, they not only drew closer, but also interacted, creating gravitational waves that disturbed the space around them. As a result of this cosmic collision, which occurred at the heart of the solar system, a massive catastrophic event took place. At the time of the collision, which scientists date to about 450 million years after the formation of the solar system, Theia and Proto-Earth collided with a force equivalent to billions of nuclear explosions. This led to the ejection of a vast amount of material into space, which later became the basis for the formation of the Moon. During the collision, the surface temperature of Proto-Earth reached thousands of degrees, melting rocks and ejecting them into the surrounding space. The material ejected as a result of the impact consisted of a mixture of rocks, metals, and other minerals, which formed a disk around Earth. This disk, rotating, gradually cooled and condensed, forming the satellite that we know today as the Moon. Research shows that approximately 3/4 of the Moon's mass consists of materials similar in composition to those found on Earth, which confirms the theory of their joint origin. According to the hypothesis proposed by scientists such as Dr. Alan Stewart from the Massachusetts Institute of Technology, this process of lunar formation took several 100,000 years before the satellite reached its final form and became stable. The Moon, as a result of this grand process, possesses a unique orbit that has been preserved for billions of years and influences the tides on Earth. This cosmic dance between Theia and Proto-Earth is not just a coincidence. It is a significant process that determined not only the shape of our planet, but also the conditions necessary for the emergence of life. There are also theories suggesting that similar collisions could have occurred with other bodies in the solar system, forming other planetary moons. Thus, the formation of the Moon became not only a unique event for Earth, but also a part of a broader process in the evolution of planetary systems. This great cosmic story, filled with energy and movement, continues to this day, and scientists continue to study its traces using modern technologies and methods. The Moon, as the only natural satellite of Earth, has a diameter of 3,400 kilometers and is located at a distance of approximately 384,000 kilometers from our planet. The formation of the Moon occurred as a result of a catastrophic collision that took place approximately 4,500,000,000 years ago, when young Earth encountered a Mars-sized object known as Theia. This impact ejected a massive amount of material into space, consisting of molten rocks and debris. These particles, orbiting around Earth, began to gradually aggregate, forming a satellite. In the first few tens of thousands of years after the collision, clouds of hot gases and dust, composed of silicates and metals, formed in the Earth's vicinity. These clouds gradually cooled and condensed. As this mass cooled, smaller particles collided and merged, forming larger clumps. These clumps, becoming denser, began to take the shape of a sphere, thanks to gravity pulling them towards the center. This process continued for millions of years. Eventually, around 100 million years after the collision, the Moon was formed, acquiring a stable orbit approximately 380,000 kilometers from Earth. The newly formed satellite was subjected to Earth's gravity, leading to its rotation around Earth and the formation of lunar craters and plains. The Moon, with a diameter of 3,400 kilometers, began to exert influence on Earth, causing tides and ebbs, which became a crucial factor in the development of life on the planet. These tides are caused by the gravitational influence of the Moon on Earth's oceans, leading to rhythmic changes in water levels. This phenomenon not only shapes ecosystems, but also affects the climate and the rotation speed of Earth, slowing it down over time. Furthermore, the Moon stabilizes Earth's axial tilt, preventing abrupt climate changes. The satellite has been a faithful companion of our planet for billions of years, its surface dotted with craters testifying to its tumultuous history of collisions. Lunar seas, formed as a result of volcanic activity, filled in low-lying areas and became smooth, dark patches on the Moon's surface. The first missions to the Moon, such as Apollo in the late 1960s and early 1970s, confirmed the presence of lunar regolith and other materials that provide valuable information about its history. The Moon continues to be an active subject of study, with scientists using modern technologies like high-resolution orbital satellites and rovers to explore its surface. Each new mission sent to the Moon opens new horizons in understanding its formation and its impact on Earth and life on it. During the late heavy bombardment period, Earth became a battlefield for celestial objects such as asteroids and comets, which continuously collided with its surface. These impacts, powerful and devastating, transformed the planet's appearance, creating new forms of relief. Each impact was not merely a catastrophe, but a moment when old landscapes were destroyed and new ones emerged. The force of collisions sometimes exceeded millions of tons of TNT, causing massive changes in tectonic plates and leading to the formation of mountains, valleys, and craters. During this time, young Earth had to endure constant attacks, and each new indentation on its surface became a testament to the relentless process of formation. Celestial bodies, upon impacting Earth, melted rocks and ejected them into the atmosphere, creating clouds of dust and gas that then settled and formed new layers of the Earth's crust. This process was not only destructive, but also creative. Volcanic activity, triggered by internal processes, could lead to the formation of new islands and continents. Shock waves from collisions created conditions for the formation of oceans, filling depressions with water and fostering the emergence of the first forms of life. One can say that each catastrophe caused by celestial objects served as a catalyst for changes that continued over millions of years. Atmospheric changes resulting from outgassings and dust could lead to sharp temperature fluctuations, creating harsh conditions on the surface. Nevertheless, these very conditions facilitated the emergence of the first microbial forms of life, which, despite their apparent fragility, managed to survive in extreme conditions and began gradually altering the composition of the atmosphere, releasing oxygen and creating the possibility for further evolutionary processes. Thus, during this period, Earth underwent continuous transformation, where each new indentation on its surface was not just a memory of destruction, but also the beginning of something new. Collisions with the cosmos not only destroyed, but also created new mountain ranges, deep oceanic basins, and even the first continents, which became the foundation for future ecosystems. This was a time when Earth, like a sculptor, shaped itself from chaos, turning the blows of fate into a grand spectacle of creation and destruction. One of the most striking examples of this process is the formation of lunar regolith, which was created as a result of constant bombardments of the moon and witnessed all these events. With each new collision, every tiny particle of lunar soil recorded the history of collisions and transformations. Thus, Earth and the moon, in constant interaction, became part of a vast cosmic theatre, where each role and each scene had its significance in the grand spectacle of our planet's existence. The atmosphere of the ancient Earth was completely unfamiliar to our perception, resembling the sky over a stormy sea. Its composition was far from what we observe today. It was primarily composed of carbon dioxide, methane, and ammonia. For the first billion years on Earth, there was almost no oxygen, creating conditions in which life as we know it could not exist. Gas molecules intersecting with each other caused constant reactions, resulting in thick cloud cover, while heavy gases accumulated in endless layers like dense fog. The sky over this primordial planet was colored in bright red and orange hues, giving it an otherworldly appearance as if it were from another world. In such an atmosphere, frequent electrical discharges occurred. Lightning, emerging from clouds, disrupted the celestial tranquility, creating a mesmerizing spectacle, but also indicating danger. These discharges could reach temperatures up to 30,000 degrees Celsius, equivalent to the surface temperature of the sun. These conditions seemed devoid of life, yet it was here, in this harsh environment, that the foundations for future biochemical processes were laid. Protoplanetary collisions created conditions for the formation of oceans, and it was in these waters that the first simplest organisms eventually emerged. However, before this, Earth remained a desolate and hostile place where only the most resilient molecules could survive. In those times, when the atmosphere was saturated with toxic gases and the surface was covered in lava, life as we understand it was merely a dream waiting for its time. Since Earth's formation around 4.5 billion years ago, it has undergone numerous changes that gradually made it habitable. Over millions of years, the atmosphere transformed, but in those distant days, it was a place where even the simplest forms of life could not survive. The sky over ancient Earth remained red and electrically charged, like a harbinger of what was to come. Primary oceans began to form approximately 4 billion years ago, when comets and asteroids containing water crashed into Earth's surface. These celestial bodies, primarily composed of ice, brought vast amounts of water into the atmosphere and onto the planet's surface, gradually filling low-lying areas and creating the first oceans. The water that filled these primary oceans had a characteristic blue-green tint due to high concentrations of minerals and chemical compounds such as iron and magnesium. These minerals, dissolved in the water, gave it a murky appearance and enriched it with various chemical substances, including hydrogen sulfide, methane, and ammonia, which became essential components for future biochemical processes. The composition of this primary water differed from modern water. It contained not only simple water molecules, but also complex organic compounds that could serve as building blocks for life. For instance, scientists have argued that such conditions facilitated the formation of amino acids and other organic molecules necessary for the development of the simplest forms of life. Research shows that the oceans contained up to 25% of dissolved salts, creating a unique chemical environment. When the oceans reached their maximum volume, their depth could reach several kilometers, and their area covered a significant portion of the Earth's surface, providing conditions for the formation of the first ecosystems. These primary oceans were also subject to intense volcanic activity, which further enriched the water with various minerals and chemical elements. Scientists like Dr. David Brown from the University of London emphasized that it was in such conditions that the most important chemical reactions took place, ultimately leading to the formation of the first organisms. Water in the primary oceans became not just a medium, but a catalyst for complex biochemical processes that eventually led to the emergence of the simplest forms of life. Research conducted in the 20th century showed that such conditions could have persisted for millions of years, allowing organic molecules to combine and form more complex structures. A crucial aspect is that these oceans, rich in chemical elements, became the foundation for the formation of the first cells, marking the beginning of life on Earth. The Earth's crust is composed of numerous mobile segments that slowly drift across the planet's surface, forming a complex and dynamic system known as plate tectonics. This process begins at a depth of about 8 kilometers, where the Earth's mantle, consisting of semi-liquid magma, exerts pressure on the upper crust. Over billions of years, these plate structures have moved, altering landscapes and forming mountain ranges, oceans, and continents. The average speed of plate movement is just a few centimeters per year. But over such vast timescales, these slow movements result in significant geological changes. For example, catastrophic events such as earthquakes and volcanic eruptions occur due to the collision or separation of plates. Plates that are constantly in motion can collide, leading to the formation of mountains, or diverge, creating new oceanic floors. The first theories of plate tectonics were proposed in the early 20th century by the German geophysicist Alfred Wegener, who introduced the concept of continental drift based on observations of the matching coastlines of various continents. Subsequent scientific research confirmed his ideas, revealing the mechanisms responsible for this movement. Using data on seismic activity, scientists determined that plate boundaries can be either convergent or divergent, creating different types of topography. At the boundaries where plates collide, powerful mountain ranges can form, as seen with the Himalayas, which continue to rise due to the collision of the Indian and Eurasian plates. Interestingly, in other areas where plates diverge, structures such as mid-ocean ridges form, where new oceanic crust is created from ascending magma. Understanding this, we can see that plate tectonics is not just a random process, but a well-organized system that has shaped our planet over millions of years. This mechanism also explains why our planet has various ecosystems and climatic zones, which have formed based on the location of continents. For instance, changes in the position of plates have influenced the climate on Earth, which in turn has affected the development of living organisms and ecosystems. Scientific research has shown that over the past 100 million years, the climate on our planet has undergone significant changes, which are also linked to the movement of plates. Ultimately, plate tectonics is the primary driver of geological processes, continually renewing and altering the surface of the Earth. An important aspect is that these movements occur within a global system that also includes the atmosphere and hydrosphere, making our planet unique in the solar system. Subduction is a process where one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This process occurs in subduction zones, which are often located at the boundaries of oceanic and continental plates. For example, in the subduction zone of Nagasaki, where the Pacific plate is descending under the Oya, tension builds up over decades or even centuries. Plates move at different speeds, typically ranging from several millimeters to several centimeters per year. When one plate descends, it does not simply disappear. It forms a so-called trench profile that can reach depths of more than 10 kilometers. Over time, pressure between the plates increases as they continue to move towards each other. This tension accumulates until it reaches a critical point, which can result in the sudden release of energy in the form of earthquakes. For instance, in 2011, a devastating earthquake struck Japan, caused by the subduction of the Pacific Plate under the Eurasian Plate. The energy released in this event was over 9 on the Richter scale. Concurrently, subduction also leads to volcanic activity. As a plate descends, it heats up and begins to release water and other volatile substances, causing the upper layers of the mantle to melt and form magma. This magma rises and can erupt onto the surface, creating volcanoes. The Krakatoa volcano in Indonesia, active since the late 19th century, is a striking example of volcanic activity linked to subduction. As a result of these processes, mountain ranges such as the Andes in South America are formed, which are the result of long-term interaction between continental and oceanic plates. However, subduction is not a linear process. It is accompanied by cyclic changes and periods of relative calm, making the prediction of earthquakes and volcanic activity extremely challenging. The complex geodynamic processes occurring in these zones are still studied by scientists such as Dr. John Hunter from the University of California, who specializes in the mechanics of subduction and its impact on the formation of the Earth's crust. Subduction also plays a significant role in the planet's carbon cycle, as carbon in the oceanic crust returns to the mantle, influencing global climate. Ultimately, the process of subduction is a crucial element of tectonic activity, continuously renewing and changing the surface of the Earth. During the process of oceanic crust formation, magma rises from the mantle through faults, creating new oceanic crust. This activity occurs at the boundaries of tectonic plates, where plates diverge, creating deep fissures on the ocean floor. The most well-known example of this phenomenon is the Mid-Atlantic Ridge, which stretches over 6,000 kilometers along the floor of the Atlantic Ocean. Here, in conditions of absolute darkness and high temperatures, magma from mantle sources rises to the surface, leading to the formation of basaltic crust. This process was first extensively described by American geologist Gary Hodge in the mid-20th century, who studied samples collected by deep-sea apparatuses. At a depth of about 3 kilometers below sea level, temperatures can reach 700 degrees Celsius, creating ideal conditions for tectonic processes. When magma reaches the surface, it rapidly cools, forming new layers of crust that gradually expand the ocean floor. This process occurs on all continents and in oceans, but underwater volcanism is generally less noticeable than its surface counterpart due to the lack of light and great depth. Nevertheless, these volcanic eruptions can create underwater mountain ranges and islands, such as the Galapagos Islands, formed as a result of volcanic activity on the eastern edge of the Pacific Plate. Unlike terrestrial volcanoes, underwater volcanoes not only erupt lava, but also water jets containing minerals that nourish unique ecosystems. These ecosystems exist in complete isolation from the rest of the world, and organisms such as black smokers depend on chemosynthesis. Over the past few decades, scientists like Dr. David Kearns from the Scripps Institution of Oceanography have conducted research showing that oceanic crust spreading also influences global climate change, as large volumes of carbon are released that would otherwise remain in the atmosphere. This interaction between oceanic and atmospheric processes demonstrates how complex and interconnected the systems on our planet are. Spreading accelerates the divergence of continents, and over millions of years, it can lead to the formation of new oceans and continents, altering the map of the world. For example, scientists suggest that in a few dozen million years, the Atlantic Ocean may significantly expand while the Pacific Ocean contracts. This process of oceanic crust spreading not only shapes the physical surface of the Earth, but also influences climate conditions, ecosystems, and even the distribution of biodiversity, creating new niches for life in the most unexpected places. The process of oceanic crust spreading continues to this day, and its effects are felt across the entire planet. Supercontinents are vast land masses that form as a result of plate tectonic processes, uniting continents into a single whole and breaking apart into smaller pieces over millions of years. This cycle of unification and disintegration, known as the supercontinental cycle, repeats approximately every 300 million years. During each such period, when land masses coalesce into a supercontinent, climate and ecosystems undergo significant changes. For instance, when continents converge, the climate becomes more uniform, which can lead to an increase in temperature and a reduction in ecosystem diversity. This creates conditions for mass extinctions, as many species cannot adapt to the new conditions. Conversely, when supercontinents begin to break apart, the climate becomes more diverse, and various ecosystems start to isolate themselves from one another. This isolation creates unique conditions for evolution, giving rise to new species and ecosystems that can only exist under specific conditions. For example, research shows that the breakup of the supercontinent Pangaea, which occurred around 200 million years ago, led to the formation of distinct flora and fauna in separate regions such as South America and Africa. Oceanic currents also play a crucial role in this process. When continents shift, ocean currents change as well, which can affect the distribution of heat across the planet. Currents like the Gulf Stream depend on the configuration of land masses and can change, leading to alterations in climate in different parts of the world. The evolution of marine life is also closely linked to the movement of continents. For instance, the isolation of certain marine ecosystems can result in the formation of unique species that are not found elsewhere. Oceanic basins that separate from one another become home to various ecosystems, each adapting to its own conditions. Thus, the process of unification and disintegration of supercontinents creates a complex network of interactions between climate, ocean currents, and the evolution of life, ensuring continuous change on the planet. Scientific research indicates that the current continental configuration will lead to a new supercontinent in approximately 300 million years, which will again alter climatic conditions and ecosystems. Pangaea was a supercontinent that existed approximately 300 million years ago, at the end of the Paleozoic era and the beginning of the Mesozoic era. Its shape resembled a giant letter P, or a half-moon, stretching from the polar regions to the equator. Pangaea united almost all the existing continents at that time, such as Laurasia and Gondwana, creating a single massive landmass. At its maximum extent, Pangaea covered an area of around 60 million square kilometers, making it the largest continent in Earth's history. The climate on Pangaea was extremely diverse, but the central regions of the continent were characterized by pronounced aridity. The interior regions were far from the oceanic waters, leading to the formation of vast deserts where temperatures could reach 38 degrees Celsius. Along the peripheries of Pangaea, near the coasts, monsoon rains were observed, providing the necessary moisture for life. These monsoons brought abundant rainfall during the rainy season, creating conditions for tropical forests and diverse flora. A temperate climate, characteristic of many modern regions, was almost absent on Pangaea, making it difficult for many organisms to adapt to such conditions. Only in certain areas, such as some coastal zones, did the microclimate allow for the existence of more diverse ecosystems. Nevertheless, the majority of Pangaea experienced extreme climatic conditions, which had an impact on the evolution of living organisms. For example, dinosaurs appeared during this period and adapted to the diverse conditions, but their development was significantly influenced by climatic changes. Pangaea began to break apart around 200 million years ago, leading to the formation of the modern continents and changes in climatic patterns, which in turn affected life on Earth. The existence of Pangaea is a significant milestone in the history of our planet, demonstrating how geological activity shapes not only the land, but also the climate and ecosystems. Approximately 200 million years ago, the process of the breakup of Pangaea began with the slow divergence of tectonic plates, causing this unified continent to start to fracture, forming new oceans and seas. Initially, Pangaea was a vast landmass surrounded by a single gigantic ocean called Panthalassa. Over millions of years, tectonic forces acting on Earth began to push continental plates in different directions. Around 190 million years ago, During the early Jurassic period, Pangaea split into two large continents, Gondwana in the south and Laurasia in the north. This division occurred slowly, and in the process, narrow seas such as Tethys began to form, gradually widening into broader oceans. Around 150 million years ago, as a result of the continuing movement of the plates, Tethys began to tear apart, creating new water spaces. And at this time, the process of forming the Atlantic Ocean began. Continents such as South America and Africa began to drift apart, creating increasingly wider spaces between them. By this time, tectonic activity had reached such a level that narrow marine straits formed between them, which over time turned into oceanic basins. This process took millions of years, and as a result, South America, separating from Africa, began to move westward, contributing to the formation of the Atlantic Ocean, which reached a width of several thousand kilometers. As the continents continued to move, significant changes occurred on the surface of the Earth. Volcanoes, active during this period, created new lands, and faults formed where plates collided or diverged. For example, around 100 million years ago, with the formation of a new ocean, the height of volcanoes on the continents changed, and new ecosystems began to form on their slopes. With changes in topography, the climate also underwent significant changes, from hot tropical regions to cold polar areas. Over time, around 80 million years ago, the process of separation became more apparent. The Atlantic Ocean continued to widen, and continents such as Europe and America moved further apart. This process was not painless. Earthquakes and volcanic activity were constant companions of the movements of the tectonic plates. Scientific research conducted in recent decades has shown that the speed of the continent's separation varied from several millimeters to several centimeters per year, resulting in the distance between continents increasing by tens of kilometers over 1 million years. Currently, we can observe the consequences of this grand process. For example, the Red Sea, which formed between Africa and the Arabian Peninsula, is a result of the divergence of these continents, and its width is now around 300 kilometers. The continuing movement of the plates today forms new geographical features. As a result of these tectonic processes, there are now many unique ecosystems that have emerged due to the separation of continents and the formation of oceans, such as coral reefs in the Caribbean Sea, which depend on a stable climate and specific oceanic conditions. The formation of the Atlantic Ocean began approximately 100 million years ago when continents began to separate from one another. Initially, there was a narrow strait between Africa and North America, which gradually widened to reach its current size of several thousand kilometers. This process was driven by tectonic movements as the plates forming the Earth's crust began to diverge. Specifically, during the early Cretaceous period, around 130 million years ago, active faulting began, leading to the formation of ridges and basins that filled with water. The most significant milestone in this process was the formation of the Central Atlantic Ridge, which became the primary source of oceanic crust formation. As the ocean widened, ocean currents also changed. Initially, warm currents like the Gulf Stream dominated, influencing the climate of North America and Western Europe by raising temperatures and creating milder winters. Meanwhile, cold currents such as the Canary Current began to affect the climate of North Africa, contributing to the formation of deserts and arid regions. These changes in temperature and salinity facilitated the evolution of marine life. The opening of new marine routes led to the migration of various fish and marine mammals, such as dolphins and whales, which began to adapt to new conditions. For example, around 30 million years ago, the expansion of the Atlantic Ocean created conditions that facilitated the development of species like the blue whale, which became the largest animal on Earth. The emergence of new ecosystems in the Atlantic Ocean led to the formation of unique biomes, such as coral reefs in the Caribbean Sea, which support a wide diversity of marine life. These reefs are home to thousands of fish, mollusks, and other marine organisms, and their existence depends directly on water temperature and quality. The increase in the volume of the Atlantic Ocean also influenced global climate changes, particularly atmospheric circulation. As a result, on the continents, tropical rainforests and savannas formed, which affected the evolution of terrestrial animals and plants. Thus, the formation of the Atlantic Ocean became not only a geological event, but also a pivotal moment in the history of Earth's biosphere, altering climatic conditions and the evolutionary development of marine and terrestrial ecosystems. Currently, the width of the Atlantic Ocean is approximately 6,000 kilometers. Volcanism is a process that occurs due to the release of internal energy from the Earth. This energy accumulates in magma chambers located beneath the Earth's crust over millions of years. As pressure increases, the magma seeks an exit, breaking through the crust via faults and cracks. This results in an eruption, during which molten rocks, known as magma, rise to the surface. There are several mechanisms by which this occurs. One of them involves the fact that as the temperature and pressure in the magma chamber increase, gases dissolved in the magma begin to expand, creating additional pressure. This pressure builds up until the crust ruptures, which can lead to catastrophic consequences. The force required to break through the crust can reach several hundred atmospheres. Typically, the eruption process occurs suddenly when magma finds a weak point in the crust. This process is similar to a compressed spring. As long as the pressure does not reach a critical value, the spring remains in a state of rest. However, once the tension becomes too great, the spring decompresses and releases the accumulated energy. Volcanism is a constant struggle between the internal forces of the Earth and the properties of the crust that hold them back. Different types of rocks form depending on the composition of the magma and the conditions under which it solidifies. For example, basalt is formed from liquid magma that cools quickly, while granite forms from magma that cools slowly underground. Volcanic activity is not limited to visible eruptions. Underwater volcanoes and hot springs are also manifestations of this process. Deep beneath the oceans, there are so-called rift zones where tectonic plates spread apart, allowing magma to rise and form new oceanic crust. According to geologists, more than 80 eruptions occur worldwide each year, some of which can have devastating consequences for the environment and human civilization. Volcanic activity also affects the climate by releasing enormous quantities of ash and gases into the atmosphere, which can significantly alter temperature conditions on the planet. One example is the eruption of the Krakatoa volcano in 1818, which caused a global cooling event known as the Year Without a Summer. Complex interactions between internal and external conditions create a dynamic atmosphere of tension on the planet, where each eruption is not just an event, but the result of multi-generational processes that continue to this day. Volcanism teaches us that the Earth is not a static formation, but a living organism that is constantly changing and reacting to internal and external influences. Currently, it is known that the vast majority of volcanoes are located along the boundaries of tectonic plates, which are dynamic zones where there is a constant struggle between the movements of the crust and the internal forces of the Earth. Trapped volcanic activity manifests as extensive lava flows that can cover vast territories. An example of this type of volcanism are the traps in India, known as the Deccan Traps, which formed around 60 million years ago as a result of one of the largest volcanic activities on the planet. These eruptions occurred over several million years, resulting in the formation of layers of basalt lava up to 2 kilometers thick in some places. The lava, flowing from cracks in the Earth's crust, slowly spreads across the surface, creating extensive plateaus that can stretch over thousands of square kilometers. As the lava accumulates layer by layer, it forms stepped structures that can be seen on many volcanic plateaus, such as the Columbia Plateau in the United States. This type of volcanism is characteristic of fissure eruptions, where lava flows out of long cracks rather than conical volcanoes. Streams of lava can be so fluid that they travel long distances, sometimes reaching over 100 kilometers from the eruption site. Upon cooling and solidification, the lava forms characteristic wavy or columnar structures visible on the surface. These massive lava flows alter the landscape, creating new landforms that can retain water and form ecosystems distinct from surrounding areas. For example, in Lake General National Park in Washington State, traps have created unique geological formations such as basalt columns, which are the result of multiple eruptions. Trap volcanic activity also plays a role in studying global climate changes, as large volumes of carbon dioxide and other gases released into the atmosphere can affect climate conditions on Earth. Ultimately, such massive eruptions can cause significant ecological changes, leading to the extinction of some species and the emergence of new ones. For instance, events associated with the Deccan traps are considered one of the factors that contributed to the mass extinction of dinosaurs, which occurred around the same time as these volcanic activities. Traps are not just geological formations, they are evidence of how volcanism can influence life on the planet over millions of years. Siberian traps, formed around 200 million years ago at the end of the Triassic period, are gigantic volcanic formations stretching over more than 2 million square kilometers, making them one of the largest volcanic regions on Earth. These massive lava flows, composed of basaltic rock, were created due to intense volcanic activity, presumably caused by the breakup of the supercontinent Pangaea. Eruptions occurred over several million years, resulting in the formation of multi-layered lava and ash deposits that in some places reach heights of up to 2 kilometers. The volcanic activity of the Siberian traps significantly influenced the global climate, creating conditions known as volcanic winter. This phenomenon was characterized by a significant decrease in temperature due to the release of large amounts of volcanic ash and gases, such as sulfur dioxide, into the atmosphere. As a result, sunlight barely pierced through the ash-laden clouds, leading to a sharp drop in temperatures and changes in climatic conditions on the planet. Studies show that the Earth's temperature could have decreased by several degrees, having a devastating impact on ecosystems and contributing to mass extinctions of species. Notably, this coincides with one of the largest mass extinctions in history, when approximately 90% of all life on the planet went extinct. During this time, the Earth was shrouded in a dark atmosphere. The sky was filled with volcanic ash, and the world was plunged into cold and darkness, creating conditions in which only the most resilient organisms could survive. There are data indicating that some types of plants and animals were unable to adapt to the changes and went extinct, while others, better adapted to harsh conditions, began to dominate in the new ecosystem. These processes laid the foundation for the subsequent appearance of new species and changes in the biosphere, which in turn influenced the evolution of life on Earth. The scale and duration of the eruptions of the Siberian traps were such that they left a noticeable mark on the geological history of the planet, creating unique conditions for the formation of new ecosystems and changes in climate for millions of years to come. Volcanic eruptions from the Siberian traps, which began approximately 300 million years ago, released a vast amount of volcanic gases into the atmosphere, primarily carbon dioxide and sulfur dioxide. These gases, upon entering the atmosphere, significantly altered its chemical composition. Carbon dioxide, which under normal conditions constitutes around 0.003% in the atmosphere, reached such concentrations that it triggered a sharp rise in global temperature. This phenomenon, known as the greenhouse effect, led to global warming, which in turn altered ecosystems on land and in the oceans. Simultaneously, the released sulfur dioxide led to the formation of acid rain, contributing to the acidification of the oceans. Given that oceans cover more than 70% of Earth's surface, this had a negative impact on marine ecosystems, particularly on calcium-based organisms such as corals and mollusks. By the end of the Permian period, when the greatest catastrophe in Earth's history occurred, the level of carbon dioxide in the atmosphere increased several-fold. This resulted in the oceans becoming acidified and their temperature rising by several degrees. Under these conditions, marine organisms, which depend on calcium for the formation of their skeletons and shells, began to die en masse. Approximately 97% of all marine species disappeared as a result of this event. Additionally, global warming led to changes in climate conditions on land. Plants that were unable to adapt to the rapid temperature fluctuations and changes in carbon dioxide levels also began to go extinct. Parallel to this, there was a gradual poisoning of the planet. Carbon dioxide accumulated in the atmosphere, causing chronic diseases in animals and humans. This was not an instantaneous catastrophe, but a prolonged process that lasted millions of years. As a result, ecosystems did not have time to adapt, leading to the extinction of numerous species. The scale of extinction was so great that scientists refer to it as the Great Dying, which marked the end of the Permian period and paved the way for the Triassic. At this time, Earth lost not only marine organisms, but also terrestrial ones, including many amphibians and reptiles. The climate became drier and hotter, contributing to the spread of deserts and the reduction of forests. This change in ecosystems also affected the distribution of existing species, leading to further extinction of those that could not adapt to the new conditions. As a result of this cataclysm, a new era in Earth's history began, during which only the most adapted species survived, forming the basis for subsequent evolution. According to paleontologists, this extinction was responsible for the disappearance of more than 200 animal and plant species. Massive extinctions are catastrophic events that periodically occur on Earth and lead to the simultaneous disappearance of a significant number of species. Over the past 500 million years, our planet has experienced at least 5 major mass extinctions, each of which caused enormous changes in ecosystems and the biosphere. One of the most famous is the end Permian extinction, which occurred around 250 million years ago. It wiped out approximately 95% of all marine species and 75% of terrestrial vertebrates. The main causes of these mass extinctions range from global climate changes and volcanic activity to asteroid impacts and changes in atmospheric oxygen levels. For example, at the end of the Cretaceous period, around 65 million years ago, a catastrophic asteroid impact in the vicinity of the modern Yucatan Peninsula in Mexico caused abrupt climate changes, leading to the extinction of dinosaurs and more than 75% of all species on the planet. These events highlight the fragility of life. Despite millions of years of evolution and adaptation, ecosystems can be destroyed in a matter of moments. Over time, each mass extinction opened up new niches for the surviving species, creating conditions for new forms of life and evolutionary experiments. For instance, after the extinction of the dinosaurs, mammals, which had previously existed in the shadows of their giant predecessors, began to actively develop and occupy new ecological niches. Statistically, the rate of extinction of modern species currently exceeds natural levels observed in the past, causing serious concern among scientists. According to estimates, 1 out of every 1,000 species goes extinct on Earth each year, which is an order of magnitude higher than the normal background extinction rate. This puts not only individual species but entire ecosystems at risk, which are crucial for life on the planet. It is also important to note that mass extinctions bring not only the destruction of species, but also the possibility of new forms of life emerging. For example, mammals and birds, which arose after the extinction of the dinosaurs, became dominant groups on Earth. Each such event leaves its mark in the geological record, and the study of these periods allows scientists to better understand the mechanisms of survival and adaptation in the face of radical changes. According to paleontologists, over the past 200 million years, Earth has experienced at least 3 major waves of extinctions, each reflecting changes in climate and ecosystems. In this context, the study of mass extinctions becomes key to understanding how organisms adapt to changes in their environment and what lessons we can learn from history to prevent further losses. The Permian extinction, which occurred around 250 million years ago, is considered the most catastrophic of all known mass extinctions, wiping out up to 96% of all marine species and 70% of terrestrial species. This event marked the end of the Permian period and the beginning of the Triassic, and its consequences were catastrophic for ecosystems. The main causes of this extinction are still not fully understood, but among the proposed factors are rapid climate change, volcanic activity, and sea level changes. One of the most well-known factors is the volcanic activity in the area of present-day Siberia, known as the Siberian Traps, where around 200 million years ago, powerful eruptions released enormous amounts of carbon dioxide and sulfur into the atmosphere. This led to a severe greenhouse effect, causing a rapid increase in temperature and changes in the chemical composition of the oceans. As a result, oxygen depletion caused the mass extinction of marine organisms such as trilobites, which disappeared completely, as well as most brachiopods and corals. On land, life faded away more slowly, but no less tragically. Groups such as megatheres, large reptiles, disappeared, along with many amphibians and early mammals. Ecosystems that were once teeming with diversity became desolate. In some places, such as the territories of present-day Ural, layers of carbonaceous rocks are found, indicating that flora and fauna could not recover for millions of years. As a result of the prolonged change in habitat, new ecosystems emerged, in which only the most resilient species survived. This extinction affected even small organisms such as microscopic algae and bacteria, which play a key role in ecosystems. It took around 10 million years for the biosphere to recover, before new species could occupy the ecological niches created by the new ecosystems we observe today. The Permian extinction served as a lesson for future generations, demonstrating how fragile life on Earth can be. While some species disappeared, others, such as the ancestors of dinosaurs, began to evolve, preparing to take the place left by the dead ecosystems. After the Permian extinction, Earth faced massive changes in ecosystems, which were significantly devastated. The destruction of approximately 95% of all marine species and about 75% of terrestrial species led to a significant simplification of food chains. During this period, only a few surviving groups, such as ammonites and certain types of fish, began to adapt to the new conditions. Approximately 3 million years after the extinction, during the Triassic period, ecosystems began to gradually recover, and ecological niches started to be filled with new forms of life. This was a kind of evolutionary reset, where creatures that previously had no chance to develop were given the opportunity to occupy free niches. Around 250 million years ago, in the beginning of the Triassic period, the first archosaurs, the ancestors of dinosaurs, appeared on land and began to dominate in the new ecosystems. These groups of animals, including such as brachiosaurs and tyrannosaurs, adapted to various environmental conditions, allowing them to occupy different ecological niches, from predators to herbivores. At this time, there was also an increase in plant diversity. The appearance of the first conifers, such as Araucaria, which became the basis of new forest ecosystems. These changes led to the formation of more complex food chains, where new species interacted with each other, creating stable ecosystems. Approximately 200 million years after the Permian extinction, during the Jurassic period, ecosystems reached a new level of diversity, and dinosaurs became the dominant class of animals on the planet. At this time, the first mammals also appeared. Although they were small and insignificant, they began their path to future dominance. Thus, on Earth, there was a radical transition from uniformity to diversity, which marked the beginning of a new era, the era of dinosaurs. At this time, such species as Stegosaurus and Tyrannosaurus, which became symbols of this period, already inhabited the planet. Impact events refer to collisions between Earth and large celestial bodies, such as asteroids and comets, which can drastically alter the conditions on our planet. These events occur with alarming regularity, and their consequences can be catastrophic. For instance, a collision with a body only a few kilometers in diameter can release energy equivalent to millions of tons of TNT. This energy can cause powerful explosions that devastate ecosystems, triggering forest fires and tsunamis. The atmosphere itself can be cleared of particles and pollutants, leading to dramatic changes in climate conditions. When such events occur, darkness descends on the planet, temperatures drop, and plants and animals struggle to adapt to the new conditions, leading to mass extinctions, as happened at the end of the Cretaceous period, when approximately 75% of all species on Earth disappeared. Impact events do not merely destroy life. They also create new ecological niches, allowing some previously unnoticed species to dominate. Scientific research indicates that such collisions have occurred throughout Earth's history, each leaving its mark in the geological record. For example, craters formed by impacts can serve as evidence of the destructive power of the cosmos. Within these craters, fossils can be found that provide insight into how rapidly and drastically the biosphere changed after a catastrophe. Scientists like David Kring and his colleagues study these craters to understand how changes in life on Earth occurred. These studies show that even small impacts can cause significant changes, including sea level changes and alterations in atmospheric composition. It is crucial to understand that Earth is constantly at risk from celestial bodies that could suddenly alter our existence. There are even models that predict the likelihood of future collisions, emphasizing the fragility of our planetary balance. Each new impact could mark the beginning of a new evolutionary stage or the end of the known world. Scientific data show that in the last millions of years, Earth has been struck by several large objects, and each of these events has left an indelible mark on our planet's history. For example, it is estimated that around 30 tons of cosmic material falls to Earth daily. And while most of it burns up in the atmosphere, large objects can reach the surface and cause significant damage. Some incidents can leave craters several kilometers in diameter, which become important objects of study. Discoveries of such craters allow scientists to reconstruct the history of impacts and their consequences, highlighting how vulnerable we are to cosmic forces. In the end, each impact is not only destruction, but also an opportunity for new life and evolution. A celestial body entering Earth's atmosphere encounters air resistance and begins to decelerate, causing it to heat up and form a glowing plasma cloud around it. Objects such as asteroids and meteors, traveling at speeds exceeding tens of kilometers per second, can release enormous amounts of energy, from several tons to billions of tons of TNT, depending on their size and speed. For instance, a meteoroid just 10 meters in diameter upon reaching Earth can release energy equivalent to a nuclear bomb explosion upon impact with its surface. This generates a shockwave that travels at the speed of sound, causing destruction over several dozen kilometers from the impact point. The shockwave compresses air and rock, creating a powerful explosion that propels molten material and debris into the atmosphere, forming a fireball visible from hundreds of kilometers away. As a result of this process, an impact crater is formed, often with a central uplift, a so-called central peak, due to the elastic rebound of the rock after the initial impact. This uplift can reach tens of meters in height and is a characteristic feature of craters formed by high-energy collisions. Seismic waves generated at the moment of impact travel across the planet and can be detected by seismographs at great distances from the impact site. For example, the Chelyabinsk meteor impact in 2013 generated seismic waves detected over 200 kilometers away, confirming the power of the impact and its environmental effects. Crater formations resulting from such collisions become significant objects for studying the geological history of the planet and may contain traces of ancient life, as well as information about the composition of Earth and its atmosphere at different epochs. By studying the structure and age of such craters, scientists can reconstruct the history of impacts and better understand the dynamics of processes occurring in space and on our planet. Chicxulub crater is located on the Yucatan Peninsula in Mexico and is considered one of the most significant geological formations on Earth. Its diameter is approximately 130 kilometers, and its age is around 65 million years old, making it a result of an asteroid impact that led to the mass extinction of dinosaurs and changed the course of evolution on our planet. The crater was discovered in 1962 when geologists noticed anomalies in the Earth's structure in this area, but its true origin was confirmed only in 1980. It is believed that the asteroid that created the crater had a diameter of around 10 kilometers and struck the Earth at a speed of approximately 60,000 kilometers per hour. The impact released energy equivalent to millions of atomic bombs, causing catastrophic changes in the climate, ecosystems, and geography of the planet. As a result of this impact, there was an instantaneous evaporation of water in nearby oceans, a release of dust into the atmosphere, and global warming. The area where the crater was located is now covered with dense jungles and surrounded by beautiful beaches. But beneath this green canopy lie the traces of the catastrophe that changed life on Earth. Fossils found within the crater provide insight into life during the period when the impact occurred. Scientists have discovered traces of ancient marine organisms and deposits that help reconstruct changes in ecosystems. The external features of the crater include ring structures formed as a result of the ejection of material during the impact. The Chicxulub crater has been the subject of numerous studies, and in recent years, scientists from different countries have continued to study it to understand how such events affect the climate and evolution of life. Each year, researchers gather here to delve into the mysteries of this catastrophe, which opens new horizons in our understanding of our planet and its history. The Chicxulub crater has become a symbol of how the cosmos directly intervenes in the destinies of life on Earth, leaving traces on its surface that will be studied for many years to come. An asteroid that collided with Earth and created the Chicxulub crater had a diameter of approximately 10 kilometers and was moving at a speed of about 16 kilometers per second. This collision occurred around 60 million years ago and was one of the most powerful events in the history of our planet. The energy released in the moment of impact exceeded all nuclear explosions produced by humanity and is estimated at 130 trillion joules. In that moment, there was an instantaneous vaporization of rocks in the impact zone, resulting in the formation of a crater with a diameter of about 12 kilometers and a depth of up to 30 kilometers. The flash of light that occurred during the collision was brighter than the sun's light and could be seen from a distance of hundreds of kilometers. As a result of the impact, a fireball was formed that ejected a huge amount of debris and dust into the atmosphere, causing massive catastrophic consequences. These debris rose into the stratosphere and even into space, creating clouds of gases and particles that then settled on the surface of Earth. The temperature during the collision reached thousands of degrees Celsius, which contributed to the melting and vaporization not only of rock formations, but also of organic materials. This process was one of the causes of the mass extinction that affected up to 70% of all living species on the planet at that time. Due to the release of a large amount of carbon and sulfur into the atmosphere, the climate on Earth changed. As a result, acid rains formed, which destroyed ecosystems and had a destructive impact on flora and fauna. According to research conducted by scientists from the University of Texas, in addition to the crater, extensive zones with kilometers of blasted and burned forests were formed at the site of the impact. Astronomers and geologists, analyzing samples of rocks extracted from the crater, found traces of high temperatures and pressures, which confirmed the theory of catastrophic consequences of this collision for life on Earth. Research shows that such an event was not unique in the history of our planet. Over millions of years, Earth has been subjected to attacks by asteroids and comets, and each of these collisions has left its mark on the geological history. The Chicxulub crater, in particular, has become an important object of study, not only because it has preserved traces of ancient processes, but also because it serves as a symbol of how extraterrestrial factors influence life on Earth. Scientists continue to study this crater, examining not only its geological aspects, but also its impact on the evolution of life as a whole. The Chicxulub impact, which occurred approximately 66 million years ago, was a catastrophic event that transformed the face of Earth and led to mass extinction. At the moment of collision, an asteroid the size of a mountain struck our planet, releasing energy equivalent to 1 billion atomic bombs dropped on Hiroshima. This energy triggered an instantaneous firestorm that engulfed areas within a few hundred kilometers of the impact site. Temperatures reached thousands of degrees, turning all living matter into ash. Forests covering vast expanses burned instantaneously, and ecosystems that had existed for millions of years crumbled like houses of cards. The fire that swept across the globe left no chance of survival for animals or plants. As a result of this catastrophic event, powerful earthquakes shook the continents. Their magnitude reached 8 on the Richter scale, causing widespread destruction, fracturing the Earth, and triggering landslides. Simultaneously, in the oceans, colossal tsunamis formed, with wave heights exceeding 100 meters. These waves swept away everything in their path, including coastal cities and vulnerable ecosystems. The impact in the oceans also caused massive water vapor releases into the atmosphere, leading to acid rain. These rains, containing sulfuric and carbonic acids, fell on the Earth, destroying the remaining plants and poisoning water sources. Within a matter of hours, the familiar world where dinosaurs and other species thrived was on the brink of complete annihilation. Creatures that had adapted to their environment for millions of years suddenly faced unprecedented conditions that threatened their existence. Consequently, around 95% of all species on the planet became extinct in a short period, leaving behind desolate landscapes and empty ecosystems. These events were pivotal in Earth's history, marking the near-complete destruction of life as we knew it. The impact of an asteroid in Chicxulub, which occurred around 65 million years ago, was a catastrophic event that led to global climate changes known as the impact winter. As a result of this impact, vast amounts of dust and aerosols were released into the atmosphere, blocking out sunlight. For several months, and in some regions even years, Earth was plunged into complete darkness, with temperatures dropping by tens of degrees. According to paleoclimatologists, the average temperature on the planet fell by 10 to 12 degrees Celsius, and in some places even more. This sudden cooling led to the destruction of photosynthesis, the primary process supporting life on Earth, as plants and algae, which produced oxygen and served as food for numerous species, stopped growing. This disrupted food chains starting from the lowest levels. Since plants died, herbivorous animals were left without food, and subsequently, carnivores that fed on these herbivores also began to perish. Approximately 1 year after the impact, the biomass on Earth decreased by 80%. This led to the mass extinction of species, particularly dinosaurs, but also many mammals, reptiles, and marine creatures. Studies show that around 75% of all species on the planet disappeared in a short period. In the oceans, where oxygen levels dropped sharply, mass die-offs of coral reefs occurred, further disrupting ecosystems that depended on these structures. The impact winter lasted from several months to several years, and its effects were felt for decades. Even when sunlight began to penetrate through the dust clouds, Earth remained cold and inhospitable. Climate changes led to the formation of desert landscapes where once there were dense forests. Scientists like Dr. David Kidder from Duke University discovered that many species that survived evolved in the harsh climate, leading to changes in ecosystems and biological diversity. This period marked the beginning of a new era for life on Earth, as mammals began to occupy the niches left by the extinct dinosaurs. Studies of deposits from this time show that life, though changed, continued to find ways to adapt to the new conditions. As a result of this catastrophic event, even the smallest organisms, such as microbes, began to develop in new conditions, eventually leading to the emergence of new forms of life that came to dominate the planet. In the end, the Chicxulub impact was not just the end of one era, but also the beginning of a new one, marked by the complete transformation of ecosystems and the adaptation of the species that managed to survive in conditions previously unheard of. The impact of the Chicxulub meteorite marked a catastrophic turning point in Earth's history, signaling the end of the era of dinosaurs, which had dominated the planet for over 150 million years. Approximately 65 million years ago, this massive meteorite, the size of a city, struck the Earth in the region of present-day Mexico, leaving a crater with a diameter of around 180 kilometers. The scale of this impact was sufficient to cause global climate changes. The collision released an enormous amount of energy, equivalent to billions of atomic bombs, leading to the formation of firestorms, earthquakes, and powerful tsunamis. Billions of tons of dust and gas were ejected into the atmosphere, blocking out the sun for months, if not years. This sudden decrease in sunlight caused a sharp drop in temperature and the destruction of photosynthesis-dependent plants, triggering a chain reaction that devastated the ecosystem. Dinosaurs, from Triceratops to Tyrannosaurs, were unable to adapt to such rapid changes. These creatures, once rulers of the land, now faced food shortages and changes in their habitat. For instance, many large herbivorous dinosaurs could not find enough vegetation, while carnivorous dinosaurs lacked food sources. The extinction event affected not only large species, but also smaller ones, whose populations could not adapt to the new climate. According to scientists, around 75% of all species on Earth perished in this catastrophic event. This marked the end of the era when dinosaurs were the dominant rulers of the planet. Fossils found show how quickly some species disappeared. For example, fossils of velociraptors and other small dinosaurs date to the last millions of years before the impact, while larger species like brachiosaurs left no traces afterward. The Chicxulub impact was not just a catastrophe, but a point of no return, severing the threads of evolution for these animals. Dinosaurs, once seemingly invincible and all-powerful, vanished from the map of living nature, making way for mammals and other forms of life that would dominate the planet in the ensuing millions of years. This transformation opened a new chapter in Earth's history, where mammals, such as the ancestors of modern humans, began to gradually fill the niches left by the dinosaurs. The Chicxulub impact was not just the end of an era, but the beginning of a new evolutionary story, where life on the planet took on entirely new forms. New ecosystems began to form based on the survivors of the changed conditions, such as small mammals that began to evolve and adapt to the new circumstances. Scientists studying this period assert that it was during this time that mammals began to exhibit the diversity of forms and adaptations that would later lead to the emergence of modern species. The geological record, including fossils and geological layers, confirms that the world after the Chicxulub impact looked entirely different from before. Small mammals, such as rodents and insectivores, were able to adapt to new conditions and occupy ecological niches that became available after the mass extinction that occurred approximately 66 million years ago. Their small size allowed them to hide from predators and find food in the changed conditions. For example, rodents that appeared during this period were able to reproduce quickly and actively utilize resources that became available after the disappearance of dinosaurs. These mammals began to develop diverse forms and sizes, which allowed them to successfully compete for food and shelter. Birds that survived the catastrophe also demonstrated remarkable adaptation. For instance, the ancestors of modern birds, such as Archaeopteryx, retained their ability to fly, which gave them the ability to move between different ecosystems and find food sources inaccessible to terrestrial mammals. Birds began to develop various beak shapes, allowing them to eat seeds, insects, and even small vertebrates. Their ability to migrate provided access to various ecosystems and resources, contributing to their global spread. Crocodiles and turtles also managed to adapt to new conditions. Crocodiles, thanks to their reptilian nature, could survive in water bodies where they found food and shelter from predators. Their thick skin protected them from drying out, and their ability to stay underwater for long periods allowed them to avoid threats. Turtles, in turn, developed strong shells that protected them from predators and the ability to slow down their metabolism, allowing them to survive in conditions of limited food. Their diet became more diverse, helping them adapt to the changed ecosystems. The period following the Cretaceous-Paleogene extinction was a time of radiation for these groups. Mammals began to actively fill ecological niches previously occupied by dinosaurs. For example, by the beginning of the Eocene, approximately 5 million years after the extinction of dinosaurs, mammals began to develop into various forms, including primates and predators such as Miocene. Birds began to develop various ecological adaptations, including aquatic and terrestrial birds that could occupy new niches in ecosystems. Crocodiles and turtles continued to evolve, preserving their unique adaptations and increasing their diversity. These groups of organisms became the main participants in new ecosystems, forming diverse biomes. For example, mammals and birds began to populate forest, steppe, and desert zones that were previously inaccessible. Crocodiles, retaining their reptilian nature, occupied the niche of predators in water bodies, while turtles became important participants in terrestrial ecosystems, influencing vegetation. Thus, there was significant evolution and adaptation of these groups of organisms, leading to the formation of modern ecosystems. As a result, approximately 30 million years later, the ancestors of modern mammals, including humans, appeared. Supervolcanoes are among the most powerful and destructive geological structures on Earth. They differ from ordinary volcanoes not only in scale, but also in the mechanism of eruption. Supervolcanoes can eject hundreds and even thousands of cubic kilometers of magma and ash in a single eruption. For example, an average eruption of a supervolcano can release from 1,000 to 10,000 cubic kilometers of material, which is several times more than what an ordinary volcano can release during its active period. These giant structures form as a result of the accumulation of magma in underground reservoirs, where pressure builds up to a critical level. When the pressure becomes too high, a catastrophic eruption occurs that can change the landscape and climate over vast areas. One of the interesting aspects of supervolcanoes is that their eruptions can lead to global climate changes. Ash and gas ejected into the atmosphere can block sunlight, causing a sharp drop in Earth's temperature, a phenomenon known as a volcanic winter. Throughout Earth's history, There have been instances where eruptions of supervolcanoes have affected the climate for several years or even decades. Such events can cause mass famines, as agriculture in affected regions is threatened. Supervolcanoes typically have enormous calderas, with diameters reaching tens of kilometers, and in some cases, they are surrounded by rings of mountain ranges formed as a result of previous eruptions. These calderas can fill with water, creating lakes that become important ecosystems. Research shows that supervolcanoes can reactivate after thousands of years, and many scientists believe that potential eruptions could occur in the future. Monitoring supervolcanoes has become an important part of volcanology, using modern technologies such as GPS and satellite imagery to track changes in their activity. Scientists study their behavior and attempt to predict possible eruptions to minimize potential risks to the population. In some cases, such as the study of the Yellowstone supervolcano, scientists have collected data on its activity over the past millions of years. These data show that the interval between eruptions can vary from several hundred thousand to several million years. The study of supervolcanoes remains a relevant topic, as their potential consequences can affect not only local ecosystems, but the entire world. It is important to note that such eruptions usually occur during periods when magma activity is building up, and this can be preceded by changes in seismic activity and land deformation. The scientific community is actively working on creating models that will help predict the behavior of supervolcanoes based on historical data and current observations. Predicting such events is crucial for protecting the population and ecosystems. Currently, active research is being conducted to understand the dynamics of supervolcanoes and their possible impact on the climate. Yellowstone caldera is a massive crater formed by several catastrophic eruptions. Its diameter is approximately 32 kilometers, making it one of the largest in the world. The main events that shaped the caldera occurred around 2 million, 1 million, and 600,000 years ago, when powerful eruptions expelled vast amounts of magma, ash, and gases, creating multi-layered deposits that can still be seen today. Inside the caldera, there is an active volcano that lifts and deforms the Earth's crust, creating underground voids filled with molten magma. This magma is not merely dormant, it continues to move, causing changes in temperature and pressure, which lead to the formation of geysers and hot springs, such as the famous Old Faithful geyser, which shoots water up to 50 meters every 80 minutes. These natural phenomena, seemingly innocuous on the surface, are actually just a small part of the hidden power beneath the Earth's surface. Every hot spring in Yellowstone National Park, from crystal clear water to vibrant thermal pools, is a manifestation of active geothermal processes occurring because the magma is only 5 kilometers below the surface. The activity of the caldera is studied using seismic research and geodetic observations, which detect even the slightest changes in the Earth's structure. Scientists from Yellowstone National Park and the US Geological Survey use specialized sensors to track movements of the Earth's crust and temperature changes that may indicate new activity. For example, in 2009, more than 30,000 earthquakes were registered, causing concern among researchers and local residents. These data show that the caldera is still active and potentially dangerous. Beneath the picturesque landscape filled with forests and lakes lies a giant magma reservoir that could cause catastrophic consequences in the event of a new eruption. Massive eruptions of the caldera could release millions of tons of ash into the atmosphere, leading to climate changes not only in the region, but worldwide. Volcanic activity in Yellowstone is not just a danger, it is a unique opportunity to understand the processes that shape our planet. Research shows that beneath the caldera is a system of faults that allows magma to rise to the surface, creating the potential for future eruptions. This power is hidden beneath the beautiful landscapes of the park, where nature appears calm and balanced, but beneath it lies a force capable of changing the world. Majestic geysers and hot springs are just a small part of a vast system where scientific research continues, trying to unravel the mysteries hidden by this natural anomaly. In this context, the Yellowstone caldera is not only a subject of study, but also a crucial object for understanding volcanic activity in general. The last major eruption of Yellowstone occurred approximately 600,000 years ago, during a period known as the Yellowstone eruption, and it was one of the most powerful volcanic events in Earth's history. This eruption resulted in the formation of a massive caldera with a diameter of about 30 kilometers. Ash and volcanic gases released into the atmosphere spread over thousands of kilometers, covering significant areas of North America. Research indicates that layers of volcanic ash were found in places like Texas and even in the eastern part of the United States, demonstrating the scale of the eruption. Ash clouds reached heights of approximately 30 kilometers, creating a spectacular sight but also catastrophic consequences for life on Earth. As a result of this eruption, known to scientists as tephra, there was a sharp change in climate on the continent. The sky over North America became dark and shrouded in ash, with sunlight barely penetrating the clouds, leading to a drop in temperature by tens of degrees Celsius. There were numerous accounts of how vegetation began to wither under the layer of volcanic material that settled on the soil, disrupting ecosystems and causing mass extinction of flora and fauna. Scientists such as Dr. John Webster from the University of California found that the climate change caused by this eruption could have lasted for several years, leading to some animal species being unable to adapt to the new conditions and going extinct. This event was a kind of cataclysm that not only altered ecosystems, but also influenced the development of human civilizations in the future. Research shows that subsequent generations living in these regions faced consequences such as food shortages and changes to their way of life. The level of ash that fell on the ground reached several centimeters in some places and left a deep mark in the geological history of the region. This eruption became a significant subject of study for volcanic activity and its impact on climate change, attracting interest from scientists worldwide, as it clearly demonstrates how volcanic activity can have long-term effects on the planet. Supervolcano Toba is located on the Indonesian island of Sumatra and is one of the largest and most dangerous volcanic systems on the planet. The Toba caldera was formed as a result of a catastrophic eruption that occurred approximately 72,000 years ago, when, according to research, the eruption released more than 30 cubic kilometers of magma. The diameter of the caldera is approximately 130 kilometers, making it one of the largest in the world. In the center of this gigantic crater lies Lake Toba, which stretches 72 kilometers in length and 26 kilometers in width. This lake, with its crystal clear water and picturesque landscapes, is surrounded by green hills and lush vegetation, creating a contrast with what lies beneath its surface. The water in the lake has an average depth of around 1,400 meters, and in the deepest place, it reaches 2,400 meters. The eruption of Toba is considered one of the most powerful in the last 2 million years and caused global climate changes that could have led to a reduction in the population of Homo sapiens. The structure of the volcano itself is unique, consisting of several layers of magma rocks formed as a result of subsequent eruptions following the catastrophic event. On the surface of the caldera, remnants of volcanic activity are preserved, such as volcanic bombs and pumice, indicating powerful eruptions. One of the most interesting features of Toba is that it remains active today, with small manifestations of thermal activity, such as hot springs and fumaroles. Scientific research in this region shows that Toba could wake up again in the future, and the potential threat of a new eruption causes concern among volcanologists. However, the landscape around Lake Toba currently appears peaceful and serene. This place attracts tourists with its beautiful views and the opportunity to relax on the shore, basking in the sun and enjoying nature. Local residents living on the islands within the lake lead a traditional way of life, earning a living through fishing and agriculture, while the volcano remains a symbol of the immense power of nature hidden beneath the peaceful surface. Studying Toba provides a unique opportunity to understand not only the geological history of the region, but also its impact on human evolution. Around the lake, there are several small villages where one can meet people with a rich cultural heritage who continue to pass down the traditions of their ancestors. Scientists continue to conduct research to understand the processes taking place under the caldera and how they may affect the future of the region and the world as a whole. The state of the volcano and its potential activity remain a focus of attention, as understanding such giants as Toba is critically important for assessing the risks associated with volcanic activity and its consequences for humanity. The eruption of the Toba volcano, which occurred around 74,000 years ago, was the most powerful known eruption in human history and, according to scientists' estimates, released approximately 35 cubic kilometers of volcanic material. This event was a true planetary catastrophe, darkening the sky for many years and causing a significant change in climate. The enormous volumes of ash and gases released into the atmosphere prevented sunlight from reaching the Earth's surface, creating dark days and nights. Specialists from the Institute of Volcanology and Seismology in Indonesia note that this darkness could have lasted up to 10 years, leading to a global cooling known as the volcanic winter. The temperature on the planet dropped by several degrees, which had catastrophic consequences for ecosystems and agriculture. Plants had difficulty surviving in such conditions, which in turn affected the food chain, as many animal species could not find enough food. It is believed that the population of Homo sapiens was reduced to a few thousand individuals, which could have led to a genetic bottleneck, the effects of which are still felt today. A study conducted by a group of scientists led by Dr. Lars Hendrickson showed that the remaining groups of people survived in conditions of limited resources, which facilitated migration and movement to more favorable regions. The recovery of the population was very slow, and it took several thousand years for humanity to return to its previous level of population. This eruption not only changed the climate, but also left a deep mark on human history, as it could have influenced the development of culture, technology, and social structure. Geologists studying the deposits formed after the eruption note that layers of ash and volcanic material can provide valuable information about how humanity adapted to these changes. Scientific research, such as the work of Professor David Sorensen, has confirmed that Toba had a significant impact on the diversity of species and human evolution, directing development towards greater resilience and adaptability to ecological changes. The release of sulfur dioxide, carbon dioxide, and other greenhouse gases caused by the eruption created conditions that contributed to long-term changes in the climate, making this event one of the most significant in the history, not only of Earth, but also of humanity. The Toba volcano continues to be an object of scientific research, and its study helps to understand how such catastrophes can affect life on the planet. The size of the Toba crater is approximately 100 kilometers in diameter, making it one of the largest craters on Earth. Scientists working on this topic continue to study samples of lava and ash to better understand the mechanisms underlying such powerful eruptions. Volcanic activity plays a significant role in altering Earth's climate by influencing the atmosphere through the release of gases and aerosols. During eruptions, volcanoes emit vast quantities of sulfur dioxide, carbon dioxide, and other gases that affect the physical properties of the atmosphere. For instance, sulfur dioxide in the atmosphere converts to sulfuric acid, forming aerosols that can reflect sunlight back into space. This phenomenon can temporarily lower the surface temperature of Earth, as less solar radiation reaches it. These aerosols can remain in the atmosphere for several days to several years, depending on their height and atmospheric conditions, creating complex climatic effects. Additionally, volcanic gases such as carbon dioxide are greenhouse gases that contribute to the warming of the planet. Carbon dioxide, when it enters the atmosphere, traps heat, leading to the greenhouse effect. This creates a balance between the cooling effect of aerosols and the warming effect of greenhouse gases. Scientific research shows that even small changes in volcanic activity can have a significant impact on climatic conditions. For example, even short-term volcanic eruptions can alter rainfall patterns, causing droughts or floods in various regions of the world. Furthermore, volcanic dust that rises to the upper layers of the atmosphere can affect cloudiness, altering condensation and cloud formation processes. This, in turn, can change the amount and distribution of precipitation. Research shows that volcanic aerosols can also increase the number of clouds, enhancing Earth's reflectivity and reducing the amount of solar radiation reaching the surface. These processes create a complex interplay between Earth's internal processes and its climate system, where each element influences the others. Therefore, Volcanic activity serves as an example of how natural processes can have a profound impact on climate, participating in global temperature changes and atmospheric conditions. Scientists continue to study these interactions to better understand how volcanic eruptions can influence climate in the long term. For instance, research has shown that an increase in the concentration of volcanic aerosols in the atmosphere can alter atmospheric circulation, which in turn affects climatic conditions in specific regions. Volcanic activity is not just a local natural catastrophe. It is a powerful factor capable of changing climatic conditions on a global scale. In this context, it is important to consider that volcanoes, by releasing gases and aerosols, create not only short-term but also long-term climatic changes that can persist for decades. The height to which these gases rise also determines their impact on climate. For example, gases that rise to the stratosphere can remain there much longer than those that stay in the troposphere. One such connection between volcanic activity and climatic changes is considered a crucial aspect for understanding global warming and its consequences for human society. Volcanic activity and its impact on climate can have both positive and negative effects, highlighting the importance of further research in this area. In the year 1816, the world encountered an anomalous climatic phenomenon known as the Year Without a Summer, caused by the catastrophic eruption of the Tambora volcano in 1815 on the Indonesian island of Sumbawa. This eruption was one of the most powerful in the last several thousand years, releasing a vast amount of ash and sulfur gases into the atmosphere. As a result, sunlight was significantly blocked, leading to a sharp drop in temperature across the entire planet. In Europe and North America, summer became cold and rainy, and in some regions, snow even fell. In June 1816, residents of New England observed temperatures dropping to -1 degree Celsius, with snow covering the ground, creating an atmosphere of strange and incorrect summer. During this time, when people usually enjoy the warmth and sun, they were forced to wear winter clothing, and in some places, even light fires in their homes. Famine became an inseparable part of this year, as the cold weather destroyed potato, corn, and other major crop harvests. In Switzerland and Germany, farmers reported losses of up to 70% of their crops. Consequently, in Europe and North America, mass food riots broke out. City dwellers, dependent on agriculture, faced food shortages, causing panic and social unrest. In some places, such as Ireland, the price of bread reached record highs, and farmers, already severely affected by the poor harvest, found themselves on the brink of ruin. People, not understanding the causes of what was happening, began to put forward various theories, including folk superstitions and religious explanations, believing that this could be a punishment for sins. Astronomers and scientists, such as Lord Byron and Francis Bacon, tried to explain the anomaly, but their efforts were unsuccessful. In some cases, such as with the poet Lord Byron, this unusual climate became a source of inspiration for creativity, and the Year Without a Summer gave rise to numerous literary works reflecting the fear and confusion of people. In the United States, particularly in the state of Massachusetts, residents began to gather in groups to discuss their problems, and many of them expressed dissatisfaction with the government, demanding action to address the food crisis. Ultimately, this year became a symbol of how natural disasters can turn against society, undermining its foundations and causing deep social changes. The consequences of the Year Without a Summer were felt for several years, as the recovery of agriculture took a long time, and those who survived this terrible period remembered it as a time when nature seemed to lose its rhythm, leaving behind only fear and bewilderment. The cultural impact of the Year Without a Summer was profound and multifaceted, permeating literature, painting, and philosophy of the time. Notably, it was during the summer of 1812, when Europe was held captive by gloomy weather conditions, that Mary Shelley wrote her famous novel, Frankenstein. This work became not only a classic, but also a reflection of the fears and anxieties of a society grappling with the aftermath of natural disasters. In Frankenstein, Shelley explores themes of creation and destruction, responsibility, and the consequences of human ambition, which can be seen as a metaphor for a humanity engulfed in chaos caused by climate change. Inspired by this atmosphere, artists of the time sought to capture the somber landscapes that became symbols of despair and hopelessness. For instance, works by John Constable and Caspar David Friedrich depicted dark and frightening scenes where nature dominated over humans, evoking a sense of futility. Friedrich, in his renowned painting, The Wanderer Above the Sea of Fog, conveys a sense of melancholy and loss, vividly reflecting the state of a society gripped by fear of the future. Literature of the time was also filled with apocalyptic sentiments. Works by Byron and Pushkin, for example, were saturated with themes of destruction and despair. In particular, in Pushkin's poem The Bronze Horseman, natural disasters such as the flood in St. Petersburg serve as a backdrop for contemplations on the fate of humanity and its place in the world. All this cultural output did not merely reflect reality, but also posed significant questions about human nature and how we respond to the challenges life presents. The events of The Year Without a Summer acted as a catalyst for artistic expression, which in turn gave birth to many masterpieces that became iconic in world culture. Thus, the influence of this year is felt not only in historical context, but also in the cultural memory of humanity, continuing to affect contemporary art and literature. Hundreds of works created during this time continue to evoke interest and make us ponder eternal truths that remain relevant today. Ice ages are large-scale phenomena where vast masses of ice, reaching several kilometers in thickness, gradually cover significant areas of continents. These processes are cyclic and recur over millions of years, causing substantial changes in landscapes and ecosystems. Ice moves slowly but inexorably, and this movement, often imperceptible over short periods, actually results in deep changes in the geography of the planet. For instance, in North America, glaciers formed the Great Lakes, which emerged from the melting of ice and subsequent filling of depressions with water. As glaciers move, erosion occurs, resulting in the formation of new landforms such as moraines, fjords, and U-shaped valleys. These ice masses can alter river courses, making them more winding and expanding the basins of water bodies. In the process, they can transport large volumes of soil and rocks, forming new ecosystems in their wake. For example, in Europe, glaciers left behind characteristic landscape features such as the Swiss Alps and Scandinavian fjords, which were formed millions of years ago. Periods of glaciation alternate with warmer intervals when glaciers retreat, opening up new lands for flora and fauna. These cycles can last for tens of thousands of years, and each new glaciation period leaves its mark in the geological record. Research shows that the last glacial maximum, which occurred around 22,000 years ago, covered much of North America, Europe, and Asia, altering the climate and ecosystems of these regions. Temperature changes caused by Earth's axial oscillations also influence these cycles. Each glaciation period is accompanied by significant climate changes, which lead to a rethinking of the familiar way of life, not only for animals, but also for humans. For example, during the last glacial maximum, Homo sapiens adapted to cold conditions, developing new hunting and gathering technologies. These changes in the environment facilitated human migration, which in turn influenced the cultural development of various peoples. Glaciers also affect sea level. When they accumulate, sea level drops, and when they melt, it rises. This leads to the formation and flooding of coastal territories, which in turn changes the distribution of populations and the development of civilizations. Thus, glaciation periods not only shape the physical landscape, but also have a profound impact on the biological and cultural diversity of the Earth. Scientific research shows that glaciation phenomena continue to influence the climate and ecosystems even in the modern world, making their study relevant and important for understanding the processes occurring on the planet. Each glaciation period leaves behind geological records that help scientists reconstruct the history of the Earth and understand how climate changes affect our future. Approximately 20,000 years ago, during the last glacial maximum, vast areas of the Northern Hemisphere were covered by ice sheets reaching thicknesses of up to 3 kilometers in some places. These ice shields extended from Scandinavia to Canada, covering significant portions of modern Russia and the United States. In Europe, glaciers formed extensive ice sheets that occupied up to a quarter of the continental surface. As a result of glaciation, the global sea level dropped sharply by around 120 meters, exposing new land areas such as the Bering Land Bridge between Asia and North America. This bridge became a crucial migration route for the first humans settling new territories. Climate change led to the formation of cold tundras and steppes in front of the ice front, where specific fauna of the glacial period thrived. These expanses were home to mammoths, hairy rhinos, and bison, which adapted to the harsh conditions, as well as giant sloths and saber-toothed tigers. Under low temperatures and a constant ice cover, vegetation was primarily composed of shrubs and low-growing grasses that could survive severe frosts. These ecosystems were dynamic, and each change in climate significantly influenced the distribution of species. For instance, as temperatures gradually began to rise, the glaciers retreated, opening new territories for animal and human migration. This process lasted for thousands of years and contributed to the formation of modern ecosystems. Meanwhile, on the territory once covered by ice, geological traces remained, such as moraines and lakes formed by the melting of glaciers. These landscape changes served as important indicators for researchers studying the impact of glacial periods on climate and biological diversity on Earth. The glacial maximum was not only a physical, but also an ecological event that shaped the character of the modern world. The last ice age, which lasted approximately from 300,000 to 10,000 years ago, was home to an extraordinary megafauna that filled harsh but teeming ecosystems. Mammoths, majestic herbivores, reached heights of around 4 meters and weighed up to 6 tons. Their long, spiraled tusks, up to 4 meters in length, were used both for competing for mates and for digging up food beneath the snow cover. Woolly rhinos, which also lived during this time, had thick fur and a layer of fat beneath the skin, enabling them to survive in cold climates. Their length was approximately 3 meters, and their weight ranged from 2 to 3 tons. These giants could traverse vast expanses of tundra, supporting ecosystems where small grasses and shrubs thrived due to their grazing and impact on the soil. Cave bears, also present during this period, were true titans among predators. An adult could weigh up to a ton and reach lengths of up to 3 meters. These bears preferred caves as shelters and actively hunted other mammals, including mammoths and rhinos. Saber-toothed cats, such as Smilodon, also dominated the hunting scene and had teeth up to 20 centimeters long. These predators hunted in groups, using their strength and agility to take down large prey like bison or young mammoths. All these species inhabited open landscapes where plains and forests alternated, creating diverse ecological niches. Thanks to their adaptations, the megafauna of that time occupied various levels of the food chain, from herbivores to carnivores. The disappearance of these animals around 10,000 years ago was linked to several factors, including climate change and human hunting. For example, hunting mammoths led to a significant reduction in their population, which also affected other predators that depended on them. Paleontologists like Professor Igor Dyatlov discovered mammoth remains in Siberia, which helped establish that these animals were not only giants of their time, but also key players in the ecosystems they inhabited. Preserved remains, including tusks and fur, provided unique insights into their behavior and way of life. Scientific research shows that the megafauna of the last ice age was a crucial element in shaping ecosystems, where each individual played its role in maintaining the balance of the surrounding environment. The melting of glaciers at the end of the Pleistocene, occurring approximately between 12 and 8,000 years ago, led to the liberation of vast territories from the ice cover, which fundamentally transformed the landscape of Earth. During this time, glaciers that had covered significant areas of North America and Eurasia for millennia began to retreat, creating new ecosystems. As the ice melted, large lakes formed, such as the ancient Lake Agassiz in present-day Canada, which once covered an area of over 1 million square kilometers. These bodies of water became important biotopes for numerous species, introducing diversity into the previously uniform tundra landscapes. The retreat of the glaciers resulted in significant changes in river systems. Rivers that had previously been frozen under thick layers of ice began to flow with renewed vigor, forming new channels and ecosystems. The global sea level gradually rose, also contributing to the formation of shallow bays and estuaries where fresh and salt waters mixed, creating rich ecosystems for fish and other aquatic organisms. With the retreat of the glaciers, the process of replacing tundra and taiga with more southern forests, such as coniferous and deciduous forests, began advancing northward. This movement of forests was accompanied by changes in flora and fauna. Species such as cherry, birch and pine began to appear in these regions, which had not been present before. As a result of this climatic change, ecosystems became more diverse and new food chains emerged. Research shows that during this time, the climate became warmer, which facilitated the development of more complex ecosystems. For example, in northern Europe, where tundra had previously dominated, mixed forests began to form, attracting many animals such as reindeer, bears, and various bird species. It is important to note that these changes did not occur instantaneously. The migration of forests and changes in ecosystems took thousands of years. For instance, in Siberia, forests began to advance northward around 6,000 years before the present, leading to significant changes in local ecosystems. These changes affected not only the vegetation and animal life, but also humans, who began to settle new territories and adapt to changing conditions. Gradually, as the area of forest cover increased, hunting and gathering activities became more active, and new cultures began to form. As a result, the melting of glaciers became a catalyst not only for ecosystems, but also for human civilization, opening new possibilities for existence and development. Scientific data indicate that during this time, in Europe and Asia, the first human settlements began to form, utilizing resources from new ecological niches, which in turn contributed to the development of agriculture and a settled way of life. There is a belief that it was during this period that the transition from nomadic tribes to more complex social structures occurred, ultimately leading to the emergence of the first civilizations. Floods caused by the melting of glaciers are catastrophic natural phenomena that can transform landscapes in a matter of days. When glaciers begin to melt, vast volumes of water accumulate in glacial lakes formed in closed basins. These lakes can be held back by natural dams of ice and sediment. But once the water pressure exceeds the strength of these dams, a catastrophic breach occurs. An example of this is the event that took place in 2003, when a breach of a glacial lake on Mont Blanc, located on the border of France and Italy, resulted in a powerful flood that swept away everything in its path, including trees and houses. The water that burst from the lake created new canyons and valleys that had not existed before, demonstrating the incredible power of nature. As a result of such floods, a unique landscape known as scabland is formed, characterized by numerous small hills and depressions created by erosion. This area appears as if water had swept across the land, leaving deep traces behind. In such conditions, as in northern Scotland, researchers have found that powerful water flows reaching speeds of up to 100 kilometers per hour eroded sedimentary rocks, forming specific geological structures. Similar processes occurred in other places, such as in the United States, where, at the end of the last ice age, around 11,000 years ago, massive floods were caused by the breach of glacial lakes in the area of the present-day state of Washington. These floods not only altered the landscape, but also triggered mass migrations of animals and people, as the available resources changed completely. Studies show that as a result of these megafloods, unique geological formations, such as the Grand Canyon, were created. Although the Grand Canyon was not formed by a single flood, it acquired its modern appearance due to numerous similar catastrophes. These events remind us of how relentlessly and quickly nature can change the landscape when it comes to such colossal forces as water breaking through barriers, creating new valleys and canyons in a matter of days. Water bursting from glacial lakes can erode rocks and create new landscapes with such force that the terrain changes dramatically, leaving behind only traces of the past. As a result of such floods, for example, in 2001 in New Zealand, where a breach of a glacial lake caused the destruction of bridges and roads, we can observe how nature, without mercy, shapes our world. Water bursting from glacial lakes leaves behind not only physical changes, but also traces in the memory of people who witnessed this destructive yet amazing process. At the end of the Pleistocene epoch, approximately 11,000 years ago, a mass extinction of megafauna occurred, affecting numerous large mammals such as mammoths, mastodons, and giant ground sloths. These animals were key elements of the ecosystems of the Ice Age, playing a significant role in maintaining the balance of nature. For instance, mammoths could reach heights of up to 4 meters and weigh up to 60 tons, with their long tusks serving as both weapons and tools for digging food out of the snow. Mastodons, with their similar but more compact form, inhabited the forests of North America and had specialized teeth for eating leaves and twigs. Giant ground sloths, known as megatheres, weighed up to 400 kilograms and used their powerful limbs to gather plants from trees. Climatic changes that took place at the end of the last ice age played a crucial role in the extinction of these species. Gradual warming led to the disappearance of ice caps and changes in vegetation, which in turn affected the feeding habits of megafauna. For example, mammoths depended on grasslands, which began to disappear due to climate change, while the forests that replaced open spaces could not provide enough food for such large animals. At the same time, the growing human population exerted pressure on megafauna. Around 15,000 years ago, people began actively hunting mammoths and other large animals, using stone tools and collective hunts. Hunting groups consisting of several dozen people could effectively burn grass to drive mammoths into traps, using tactics that led to mass kills. This pressure, combined with natural factors such as climate change, led to the disappearance of an entire complex of species. As a result, by the 19th millennium, megafauna in North America and Eurasia had almost disappeared. Studies have shown that by this time, around 70% of large mammals, including species like the shaggy rhinoceros and the saber-toothed tiger, had gone extinct. Paleontological findings, such as those in Los Angeles and Alaska, confirm that megafauna existed in these regions during the beginning of the Holocene epoch, but then disappeared. Paleontological discoveries indicate that the last mammoths died on Wrangel Island around 4,000 years ago, making them some of the last representatives of megafauna on the planet. These extinctions did not just alter ecosystems, but also left their mark on the culture and mythology of the people of that time. Images of mammoths and other megafauna appear in cave paintings, reflecting how people perceived these animals. While some researchers argue that human activity was the primary cause of extinction, others emphasize the importance of climate changes that created conditions for catastrophe. It is important to note that the combination of these factors led to the disappearance of megafauna, shaping new ecosystems that we observe today. As a result, megafauna, once inhabiting the Earth, left behind only fossils and myths. But their extinction marked a significant milestone in the history of our planet. Scientific research continues to reveal details of this mysterious era, and each new discovery helps us better understand how the interaction of climate change and human activity can shape the fate of entire species. Meteorite craters serve as vivid evidence of Earth's collisions with cosmic objects such as asteroids and comets. They form unique geological structures that are preserved in the layered crust of our planet, indicating the constant interaction between Earth and the cosmos. The study of these craters allows scientists not only to reconstruct the history of collisions, but also to understand how such events influenced the development of life on Earth. Each crater formed as a result of an impact is a temporal capsule containing data about the physical and chemical conditions at the moment of collision. For instance, a collision with the power equivalent to the explosion of millions of tons of TNT releases a tremendous amount of energy, leading to the formation of a crater and the ejection of particles into the atmosphere that can affect Earth's climate. In the geological record, such events are recorded as layers containing unique minerals and fossil remains that help scientists establish the temporal and spatial scales of catastrophes. A notable example is the iridium layer found at the boundary between the Cretaceous and Paleogene periods, which served as evidence of a collision with an asteroid that caused the mass extinction of dinosaurs approximately 65 million years ago. The study of meteorite craters shows that Earth is not protected from cosmic threats. Millions of micrometeoroids enter the atmosphere daily, many of which burn up before reaching the surface, but some can cause catastrophic damage. Crater sizes vary from small ones a few meters in diameter to giant ones exceeding tens of kilometers. For example, the Chicxulub crater in Mexico, with a diameter of about 180 kilometers, was formed around 65 million years ago. The discovery of such craters in various parts of the world allows scientists to reconstruct the history of collisions and assess potential future threats. The application of radiometric dating methods, such as argon-argon or uranium-lead dating, enables the precise determination of the age of craters and their association with specific geological events. It is important to note that many known craters are hidden under layers of soil or water, and their discovery depends on modern technologies such as satellite imagery and geophysical methods. Thus, meteorite craters are not just geological formations, but important archives that preserve evidence of how Earth interacts with cosmic forces, highlighting its vulnerability to extraterrestrial threats. There are even hypotheses that periodic impacts of large celestial bodies can cause mass extinctions, altering ecosystems and climate on the planet. To date, more than 300 meteorite craters have been registered on Earth, and their study continues to reveal new horizons in understanding the geological history of our planet. Meteor Crater, located in the state of Arizona, is one of the most impressive meteorite craters on Earth, with an age of approximately 50,000 years. With a diameter of about 1 kilometer and a depth of around 200 meters, it serves as a striking testament to the power of cosmic collisions. This crater was formed by the impact of a meteorite weighing approximately 30 tons, which struck the Earth at a speed of around 20 kilometers per second. Visually, the crater is breathtaking. Its edges drop vertically downwards, revealing a wide view of its floor, covered with debris and sand that were ejected as a result of the impact. Standing at the edge of the crater, a person feels small, like an ant on the edge of a gigantic funnel created by nature over a short period of time compared to the geological history of the planet. The scale of this event is astonishing. Meteor Crater is not just a hole, but a true wound on the Earth's surface, reminding us of how vulnerable our planet is to extraterrestrial threats. Having retained its shape and structure for thousands of years, the crater has become a subject of study for many scientists, among whom Dr. Edward Charles stands out, who has repeatedly emphasized the importance of this place for understanding meteorite activity and its effects on Earth. The crater not only attracts tourists, but also serves as a significant object for geological research, allowing scientists to study the processes that occurred after the impact and analyze the minerals in its walls. It is interesting that rare mineral samples, such as trinitite and chondrites, were found in the crater, which provide insight into the composition of the meteorite and its interaction with the Earth's crust. Meteor Crater is not only a geographical landmark, but also a real open-air museum, telling the story of cosmic catastrophes that have shaped our planet over millions of years. Its walls reveal layers of soil, each telling its own story, like pages of a book where events on Earth over centuries are recorded. The crater embodies the power of nature, reminding us that even the largest and seemingly unshakable structures can be destroyed in an instant. Its size and preservation make it a unique object of study not only for geologists, but for anyone interested in the history of our planet and its interaction with the cosmos. The Popogai crater in Siberia is one of the largest impact craters on Earth, with a diameter of 124 kilometers and an estimated age of 46 million years. This crater formed as a result of a meteorite impact, and its size and the consequences of the impact are truly impressive. It is located in a remote area surrounded by taiga forests and rivers, making it difficult to access for most travelers. The road to the crater passes through wild nature, where one can encounter rare species of animals and plants that have preserved their pristine form. These places hold not only natural secrets, but also traces of a cosmic catastrophe that left a deep mark on the history of our planet. Inside the crater, scientists have discovered unique impact diamonds, which formed under the influence of extreme temperatures and pressure during the impact. These diamonds differ from ordinary ones. Their structure and composition indicate that they formed under conditions not accessible to ordinary geological processes. Research has shown that impact diamonds contain inclusions of other minerals that also formed as a result of the impact. The unique properties of these diamonds have attracted the attention of geologists and mineralogists from around the world. In particular, Russian geologist and mineralogist Alexander Kostyuchenko conducted research in this area, studying the crystalline structure and chemical composition of these rare formations. It is worth noting that the Popogai crater is not only of geological interest, but also an object of study for climate changes that occurred after the impact. It is believed that the consequences of the meteorite fall could have led to mass extinctions, altering the ecosystem of the planet. The bottom of the crater contains deposits that have preserved traces of the animal and plant world of that time. For archaeologists and paleontologists, this is a real treasure trove, where each layer of soil can tell a story about life on Earth in different epochs. Scientists continue to conduct excavations and research to better understand how this catastrophic impact occurred and what changes it caused in the surrounding environment. As a result, the Popogai crater is becoming an increasingly interesting object for scientific research, attracting the attention not only of geologists, but also of ecologists, historians, and even astronomers. This crater is not just a depression on the surface of the Earth, but a testament to the majestic and destructive forces of nature that have shaped and continue to shape our planet. It is interesting to note that the Popogai crater is located on one of the largest meteorite fields in the world, where more than 200 meteorites have been described as having fallen on the territory of Siberia. The Tunguska event occurred on June 16, 1908, when a cosmic body, likely a meteorite or comet, exploded in the atmosphere over the Siberian taiga. This explosion released an enormous amount of energy, equivalent to several megatons of TNT, comparable to the power of nuclear weapons. The shockwave destroyed approximately 2,000 square kilometers of forest along the river Vitim, felling more than 25 million trees. The extent of the destruction was such that local residents within a radius of tens of kilometers felt earthquakes, and in some places even witnessed bright flashes of light. However, despite the scale of the devastation, no craters were found, as is typically the case with meteorite impacts, adding to the mystery of this event. Scientists and researchers have been trying to unravel the mystery of the Tunguska event for over 100 years, conducting expeditions to remote and sparsely populated regions of Siberia in search of evidence that could explain what happened. These investigations are complicated not only by the wild nature of the region, but also by its harsh climate, where temperatures can drop to minus 40 degrees Celsius in winter and rise to 30 degrees in summer. As a result, access to the site of the event is limited, and many expeditions face difficulties in organizing their work. The first systematic studies of the region began in the early 1930s, when a Soviet expedition led by academician Fyfe May Obruchev ventured into this mysterious area. They collected soil and wood samples, studied the local vegetation and topography, but no evidence confirming the theory of a meteorite explosion was found. Numerous hypotheses about the nature of the event have emerged in the scientific community, ranging from gas explosions to collisions with invisible black holes. In 1999, when a Russian group of scientists revisited the site of the explosion, they discovered strange anomalies in the soil and high levels of radiation, further fueling interest in this topic. Over the years, more than 1,000 scientific articles have been published. But the final explanation for the Tunguska event remains an unsolved mystery that continues to attract researchers from around the world. In the latest research conducted in 2020, scientists used satellite technology to analyze the area and discovered unusual signs that could indicate possible remnants of the cosmic body. But the final results are still pending. The Tunguska event serves as a vivid example of how, even in the age of advanced technology, we can encounter the unexplained. And this underscores just how much we still do not know about our planet and the cosmos in general. February 15, 2013 became the day when the sky over Chelyabinsk suddenly lit up with a bright flash. At 13:08 local time, a meteorite weighing around 17 meters and approximately 17,000 tons entered Earth's atmosphere at a speed of about 18 kilometers per second. This event caused a powerful explosion, equivalent to a 20-kiloton TNT blast, which resulted in a shock wave that shattered windows in more than 17,000 buildings and left over 1,500 people injured, mainly from glass fragments. The sudden shock disrupted the peaceful morning of the city's residents, as the brightness of the flash was visible from hundreds of kilometers away, serving as a reminder that cosmic threats can intrude into everyday life at any moment. After the explosion, emergency services, police, and local residents arrived at the scene, bewildered by what had happened. In the days following the impact, search teams consisting of volunteers and scientists began scouring the area around Lake Chebakul, where it was believed that fragments of the meteorite might have fallen. As a result of the search, numerous small fragments were found, with the largest weighing around 1.5 kilograms. The analysis of these samples allowed scientists to gain unique insights into the composition of the meteorite, which belongs to the class of chondrites. This discovery provided a better understanding of the processes that occurred in the early solar system. Moreover, the Chelyabinsk meteorite was the first large meteorite to be recorded and documented using video cameras. Numerous recordings from car dashcams and observations by ordinary citizens helped to create a complete picture of its path through the atmosphere. It is astonishing how a single moment can change humanity's perception of the cosmos, as many had not previously considered how vulnerable we are to cosmic threats. Chelyabinsk became a symbol of an unexpected cosmic intrusion into the life of modern man, reminding everyone that we live on a planet that is not protected from sudden catastrophes. Scientific communities around the world began to reassess their strategies for asteroid monitoring, leading to several international initiatives aimed at identifying potentially dangerous objects. The significance of this event is underscored by the fact that it also sparked discussions about the creation of early warning systems for possible cosmic threats. With each passing year, as we gaze at the stars, we should remember that they can be not only a beautiful sight, but also a source of danger, capable of crashing down on us at any moment. The Chelyabinsk meteorite served as a reminder that the cosmos is always nearby, and its mysteries can disrupt our familiar reality at any moment. Tsunamis are giant waves that can occur due to various underwater phenomena such as earthquakes, landslides, or meteorite impacts. The main mechanism behind the formation of tsunamis is a submarine earthquake, when tectonic plates suddenly shift, causing a sudden rise or fall of the ocean floor. This process can generate waves that travel at colossal speeds, reaching over 100 kilometers per hour in open ocean. Interestingly, in open water, a tsunami can be virtually invisible, with a height of only a few dozen centimeters. However, when the waves approach the shore and encounter shallow water, their speed decreases and their height increases, sometimes reaching several dozen meters. This transformation is one of the most dangerous aspects of tsunamis, as a calm ocean can suddenly become a destructive force. If the wave is caused by a submarine landslide, it can be even more unpredictable. For example, when large masses of Earth collapse into the ocean, waves can accumulate energy, striking coastal areas with unimaginable force. Impacts of cosmic bodies in the ocean can also cause tsunamis, creating waves that can destroy everything in their path. Scientists studying tsunamis note that for more accurate predictions, many factors must be considered, including water depth, geological features, and even weather conditions. Typically, a tsunami warning arrives too late, as waves can reach the shore in just a few minutes after their formation. This makes tsunamis one of the deadliest natural disasters, capable of destroying entire cities and taking thousands of lives. For instance, in 2004, a tsunami in the Indian Ocean claimed the lives of more than 200,000 people in 14 countries, demonstrating the scale of destruction that this natural force can cause. Tsunamis do not have a clear seasonality and can occur at any time, making them even more dangerous. It is important to understand that even if the open ocean appears calm, underwater processes can accumulate power that will be unleashed at the most unexpected moment. Waiting for a tsunami can be a real test, as a wave hidden beneath the surface rushes towards the shore, ready to crash with the power to change the landscape forever. It is important to remember that for each region at risk of tsunamis, special early warning systems have been developed that can help save lives. However, even with such systems, the speed and force of tsunamis remain insurmountable factors. Scientists continue to study tsunamis and their mechanisms to better understand how to predict such disasters and minimize their consequences. For example, in 2017, research was conducted that showed that the behavior of waves can depend on the depth of the ocean floor and its shape, opening new horizons for predicting the behavior of tsunamis. On December 26, 2004, one of the most devastating tsunamis in history occurred, triggered by a powerful earthquake with a magnitude of 9 in the Indian Ocean, near the coast of Sumatra, Indonesia. This earthquake, which occurred at a depth of around 30 kilometers and with a length of more than 1,000 kilometers, caused a giant wave that began its movement at a speed of around 400 kilometers per hour, comparable to the speed of a jet aircraft. The first wave reached the shores of Indonesia just 15 minutes after the earthquake, but its full destructive impact was felt when the waves began to strike other countries, including Thailand, Sri Lanka, India, and the Maldives. In Thailand, a popular tourist destination, the wave reached heights of up to 15 meters, sweeping away hotels and beaches and claiming the lives of thousands of people. In Sri Lanka, where the wave hit just 30 minutes after the earthquake, the wave reached heights of 30 meters, resulting in catastrophic destruction and the deaths of more than 30,000 people. In some areas where the seabed rose sharply, the waves could increase in height, creating powerful and destructive flows that swept everything in their path. The terrain and the shape of the coastline also played a significant role. In bays and inlets where the seabed rose, the waves could reach enormous heights, while in open areas, their height could significantly decrease. Thus, the tsunami continued its movement across the Indian Ocean and reached the shores of Eastern Africa within a few hours, where its effects were felt, although to a lesser extent, with wave heights of only 1 to 2 meters. In total, according to various estimates, the tsunami claimed the lives of more than 260,000 people, leaving millions homeless and destroying entire communities. The recovery process took years, and the countries affected by this disaster launched large-scale humanitarian operations to assist the survivors. Scientific research into the aftermath of this tsunami continues, and it has served as a catalyst for the development of more effective early warning systems in the Indian Ocean. The tsunami of 2004 caused significant damage to the ecosystems along the coasts, particularly in countries like Indonesia, Thailand, and Sri Lanka. Mangrove forests, which served as natural barriers against waves and provided habitats for numerous species, were severely affected by the powerful water surges that washed away a large part of their roots and trees. According to ecologists, in some regions, the damage reached up to 70% of the original mangrove forest area. These forests not only protected against erosion, but also served as homes for various animals such as fish, crabs, and many birds. The destruction of mangroves led to a decrease in biodiversity and worsened conditions for local fishermen who relied on these ecosystems for their livelihood. Coral reefs, one of the most beautiful and diverse biomes, also suffered from the tsunami. As a result of the strong waves, the reefs were destroyed, and their recovery requires decades. Research by scientists like Dr. Kenneth Hayes showed that the recovery of coral ecosystems is extremely slow, and only in some areas did the reefs begin to show signs of regeneration more than 10 years after the disaster. Diseases of the corals caused by stress from changes in water, such as temperature increases and salinization, exacerbated the situation. Salinization of agricultural lands became another serious problem, as seawater penetrated the soil, making it unsuitable for traditional crops like rice and coconuts. In some places, the salt content in the soil increased by 15 to 20%, leading to significant economic losses for farmers. The landscape changes were no less dramatic. The coasts experienced erosion, and many areas were permanently altered. Nature began to slowly recover, but this process requires time. In some places where once there were dense forests, now only barren areas with sparse vegetation can be seen. Scientists note that the recovery of ecosystems can take from 20 to 100 years, depending on the conditions. Some plant and animal species that disappeared after the disaster may not return, leading to irreversible changes in the ecosystems. For example, in Indonesia, the disappearance of local sea turtle species is observed, which cannot find suitable nesting grounds due to coastal erosion. The restoration of ecosystems requires not only time, but also efforts from local governments and international organisations involved in projects to restore mangroves and corals. It is important to note that restoration will not be complete without the participation of the local population. Since the early 2000s, local residents have been actively involved in projects for planting new plants and restoring reefs, understanding that their efforts determine the future of their communities. In projects like the Coral Gardens in Thailand, local fishermen plant corals to help restore the ecosystem, which also increases the fish catch in these areas. The restoration of ecosystems is a long-term project requiring a comprehensive approach and cooperation at all levels. In 2020, new coral colonies were discovered in some areas, which began to grow on previously damaged reefs, giving hope for the restoration of marine life. Paleotsunamis are ancient tsunamis that have left significant traces in the geological record. Geologists use several methods to detect and interpret the deposits left by these tsunamis. For example, in 2006, a team of scientists led by Dr. Kim O'Connor from the University of Washington conducted research on the Washington coast and discovered layers of sand that were deposited by a powerful tsunami. These layers often have distinctive features. They contain larger particles and differ in color from neighboring deposits. By studying these layers, scientists can accurately date the events using radiocarbon dating and stratigraphy. As a result of such research conducted in 2017 on Hokkaido Island in Japan, it was established that ancient tsunamis occurred approximately 2,000 years ago. It is also important to note that geologists can analyze not only the deposits on the coast, but also data collected from the ocean depths. In 2015, in the region of the Pacific Ridge, samples of sediments were collected that showed that powerful tsunamis occurred with a periodicity of about 300 years. This discovery allowed for a more accurate assessment of the risks associated with modern tsunamis and helped in the development of protection strategies. The analysis of deposits allows not only to determine the frequency and scale of ancient tsunamis, but also to understand what natural disasters could have caused these waves. For example, in 2008, researchers from Osaka University found evidence that some tsunamis were caused by underwater earthquakes, while others could be the result of the collapse of underwater slopes. These data help create a more complete picture of how and why disasters occurred in the past. Comparing data on paleotsunamis with contemporary events also helps in predicting future risks. For example, in 2009, a study conducted by scientists from the Australian National University found that some regions prone to tsunamis have similar geological conditions to those observed in areas where strong earthquakes occur. This knowledge allows for better preparation for potential catastrophes. Modeling wave processes and assessing potential damage are also based on data on paleotsunamis. In 2013, a team of scientists from Boston University presented a model based on data collected over many years, which showed that even small underwater earthquakes can cause significant waves under certain conditions. These data are important for developing early warning systems that can save lives. Geological research on paleotsunamis continues, and with each new discovery, we gain a deeper understanding of these powerful natural phenomena. For example, in 2020, on the coast of California, a new stratigraphic unit was discovered that confirms the presence of an ancient tsunami that occurred around 7,000 years ago. This information adds another layer to our understanding of the frequency and scale of such events in the past, which, in turn, helps us better prepare for future catastrophes. It is important to note that the study of paleotsunamis is not just a study of the past, but an active process that has a direct impact on the safety and protection of the population today. Earthquakes are sudden and powerful tremors of the Earth's crust, caused by the rapid displacement of blocks under immense pressure. These tectonic processes occur at the boundaries of lithospheric plates, which can move in different directions. When the tension between the plates exceeds their strength, a rupture occurs, and the energy stored in the Earth is released as seismic waves. There are several types of these waves. P waves, which travel the fastest and pass through both solid and liquid media, and S waves, which can only move through solid materials. P waves compress and expand, creating sensations similar to jolts, while S waves cause more noticeable lateral oscillations that can cause damage on the surface. As seismic waves radiate from the epicenter, their energy decreases with distance, but this does not make them safe. Even at significant distances from the epicenter, vibrations can cause buildings and infrastructure to collapse, especially if they were not designed to withstand seismic loads. For instance, in Japan, tall buildings are constructed according to seismic standards, but even they may not withstand a strong earthquake caused by unexpected tectonic shifts. It is important to note that earthquakes can occur at any time and in any place, making them particularly dangerous. Scientists cannot accurately predict the exact time or location of tremors, adding an element of unpredictability to this natural phenomenon. Earthquakes can range from mild, causing only slight tremors, to devastating, resulting in significant loss of life and property. Each level of magnitude has its own characteristics. For example, an earthquake with a magnitude of 5 to 6 can cause damage up to 100 kilometers from the epicenter, while tremors with a magnitude greater than 7 can destroy entire cities. For example, in the year 2000, an earthquake with a magnitude of 7.8 in Greece caused significant damage in Athens. The effects of earthquakes can be diverse, from cracks in the ground and building collapses to tsunamis caused by underwater shifts. These phenomena demonstrate the close connection between tectonic processes and their impact on human life. Hundreds of thousands of people die annually due to earthquakes, making the study of their mechanisms and consequences crucial for our safety. For example, in 2004, a catastrophic earthquake in the Indian Ocean with a magnitude of 9.0 triggered one of the most devastating tsunamis in history, resulting in the loss of more than 200,000 lives. Underwater earthquakes can have equally devastating consequences as their terrestrial counterparts, underscoring the need to understand all aspects of earthquakes. There are numerous technologies for monitoring and analyzing seismic activity, but none can guarantee protection from an unexpected blow. The Great Lisbon earthquake occurred on November 1st, 1755, with a magnitude of around 8. This catastrophic event affected not only Lisbon, but also many other regions of Portugal and even parts of North Africa. As a result of the earthquake, more than 30,000 buildings were destroyed, including the famous Church of St. Nicholas and numerous other historical landmarks, leading to the death of approximately 60,000 people. Soon after the main shock, a powerful tsunami struck, with waves reaching heights of more than 30 meters, which flooded coastal areas and exacerbated the already catastrophic situation. The tsunami destroyed not only port facilities, but also many residential buildings and public structures, increasing the number of victims. Fires that broke out due to the earthquake engulfed the cities and continued to devastate Lisbon for several days, destroying many neighborhoods, including the Royal Palace. The Portuguese government faced severe consequences. The country was on the brink of economic collapse, and the reconstruction of the city required significant efforts and resources. This event sparked intense philosophical debates across Europe. Philosophers such as Voltaire and Rousseau began to actively discuss questions about the nature of evil and divine providence, questioning the idea that the world is governed by a benevolent and just deity if it allows such terrible catastrophes. For example, Voltaire used this earthquake as an example of the absurdity of optimism in his work, Candide, stating that despite all efforts, the world cannot be a good place. In response to this catastrophe, scientists began to take seismic activity more seriously. The first scientific studies on earthquakes emerged, laying the foundation for the further development of seismology as a science. The reconstruction of Lisbon also served as an example of how a catastrophe can change social and cultural structures. Architectural projects for the new Lisbon, such as those by architect Marquis de Pombal, demonstrated a new approach to construction, emphasizing the importance of earthquake resistance. Measures of safety, such as the use of iron structures and improved city planning, became the norm for future generations. This earthquake also played a significant role in the development of insurance systems, as many people lost their homes and means of livelihood. As a result, Lisbon became not only a symbol of destruction, but also an example of how society can adapt and change under the pressure of natural disasters. Reconstruction efforts lasted for many years, and by the end of the 18th century, Lisbon began to look like one of the most modern cities in Europe. with new streets and buildings designed with lessons learned from this catastrophe. Around the same time, the first attempts were made to create maps of seismic activity, which became an important step in understanding and predicting such events in the future. On the night of April 22nd to 23rd, 1906, San Francisco experienced one of the most devastating earthquakes in the history of the United States. The epicenter was along the San Andreas Fault, which stretched over 1,000 kilometers. The earthquake measured 7.1 on the Richter scale and lasted about a minute. This was not just a series of tremors. It was a true catastrophe that shocked the city's residents. In the city center, buildings began to collapse like playing cards. Entire neighborhoods were wiped off the map. Approximately 80% of the buildings in San Francisco were destroyed or damaged. But the earthquake was not the only cause of the destruction. Soon after the tremors, massive fires broke out due to damaged gas pipes and stoves. The fire raged with such intensity that it engulfed entire districts, destroying everything in its path. Firefighters were overwhelmed, as the water in the reservoirs had run out and the streets were blocked by debris. The fires raged for 3 days, and it is estimated that they destroyed more than 300,000 buildings. As a result of the earthquake and the subsequent fires, more than 3,000 people lost their lives, and another 12,000 were left homeless. Approximately 400,000 residents were forced to flee, many of whom sought refuge in camps set up on open spaces and parks. Firefighters, working tirelessly, were mostly able to prevent the spread of the fire, while the buildings burned to the ground. The situation in San Francisco resembled a scene from a horror film. Streets were filled with panic. People's cries mixed with the sound of collapsing structures and the roar of the fire. Crime rose amidst the chaos, with looting and violence becoming commonplace. The city, once considered the jewel of California, was reduced to ruins. The government and charitable organizations began collecting funds and resources to help the victims. But the city's recovery took more than 10 years. The earthquake's aftermath not only resulted in the physical destruction of San Francisco, but also led to a change in the approach to construction in earthquake-prone areas. Experts began developing new standards and technologies to make buildings withstand such catastrophes. The study of the earthquake's consequences also led to the creation of modern early warning systems for earthquakes. Engineers and architects began actively developing seismically resistant structures after devastating earthquakes like the one in San Francisco in 1963, which claimed over 3,000 lives and left many homeless. The focus shifted to creating buildings that could adapt to seismic activity. One of the key technologies used in design is the use of dampers, which help absorb and dissipate energy from seismic waves. For instance, in 2000, the Tokyo Skytree, a 630-meter-tall skyscraper, was built in Tokyo and is equipped with a damping system that allows it to withstand strong earthquakes. Flexible structures, such as soft floors, became an essential element of seismic-resistant design. These floors can deform without collapsing, allowing buildings to bend during earthquakes. Scientific research conducted in 1988 showed that buildings with rigid frames are more likely to collapse during earthquakes than their flexible counterparts. Additionally, engineers began using specialized materials like high-strength steels and composites to provide the necessary strength and lightness of the structure. For example, in 1999, the Wilshire Grand, a 341-meter-tall skyscraper in Los Angeles, was built using a combination of lightweight concrete and steel structures, enabling it to withstand strong seismic activity. The use of computer modeling and seismic tests became an important aspect of developing safe buildings. Engineers can simulate the behavior of structures under various seismic conditions and make necessary adjustments before construction begins. In 2000, a new seismic safety code was implemented in California, requiring builders to conduct such tests for all new buildings, which significantly reduced the risk of destruction and loss of life from earthquakes. In recent years, technologies based on inertial masses have also been used, which help stabilize buildings during earthquakes. These masses can be installed on upper floors and move in the opposite direction to the seismic waves, thereby neutralizing their effects. The use of such technologies not only helps preserve buildings, but also reduces the stress experienced by people inside. In 1983, Japan, following a series of devastating earthquakes, established a system for monitoring seismic activity, which helps architects and builders plan new projects based on local conditions. As a result of these measures, buildings designed with seismic resistance can not only save lives, but also significantly reduce economic losses from destructive natural phenomena. For example, in 2010, in Chile, after an earthquake of magnitude 8.3, more than 7,000 buildings constructed according to modern standards remained virtually undamaged. Early warning systems for earthquakes consist of complex networks of seismographs that operate in real time, detecting even the slightest tremors of the earth. These devices, installed in strategically important locations, can detect even the weakest seismic waves. For instance, in Japan, a country known for its seismic activity, there is an extensive network of over 3,000 seismographs covering the entire territory. Each of these seismographs can react to changes in milliseconds, allowing the system to instantly process data and transmit signals about potential threats. Special algorithms developed by Japanese scientists analyze the received data and can predict the intensity of an earthquake with high accuracy. For example, the system can determine that powerful earthquakes with a magnitude of more than 5 points may occur in a few seconds, and at that moment, automatic warnings are activated. These signals are transmitted through mobile phones, television, and even through special loudspeaker systems installed in public places. In Japan, for example, the J Alert system can warn the population 30 seconds before the start of destructive tremors, which, at first glance, may seem like a small amount of time. But in practice, it can save thousands of lives. It is important to understand that for every additional second before the start of an earthquake, people can take shelter in safe places, such as specialized shelters or under tables and other reliable structures. In Chile, after the powerful earthquake of 2010, with a magnitude of 8.8, the government introduced an early warning system that includes not only seismographs, but also satellite technologies for monitoring the Earth's surface. This system allows not only to predict earthquakes, but also to track their consequences, which is crucial for effective evacuation and minimizing damage. As a result, regular drills and evacuation exercises have made Chileans more aware of actions in emergency situations. In Silicon Valley, in the United States, researchers are developing new technologies that use artificial intelligence to improve the algorithms for processing seismograph data. These innovations can significantly increase the reaction speed of the systems, allowing for earlier warnings about earthquakes. In 2020, scientists from Stanford University presented a model that can predict earthquakes with an accuracy of 90% 20 seconds before their onset. This speed may seem insignificant, but in conditions where every second counts, it can become a decisive factor. Early warning systems for earthquakes are actively developing and improving worldwide, and each new technology brings hope for reducing tragedies associated with destructive seismic events. For example, in Turkey, a system has been implemented that, in addition to standard warnings, also educates the population on how to react correctly in case of an earthquake, providing information about safe places and necessary actions. As a result, such systems not only minimize losses, but also increase the overall preparedness of the population for possible disasters. The climate of Earth has changed over millions of years, passing through cycles that can be conditionally divided into greenhouse and ice age states. These fluctuations are linked to numerous factors, including changes in atmospheric composition, tectonic processes, solar activity, and ocean currents. For instance, during the Paleocene epoch, the planet's temperature was significantly higher than today's, facilitating the development of tropical forests even in latitudes where deserts now lie. At that time, the level of carbon dioxide in the atmosphere reached values exceeding 800 parts per million, creating conditions for the greenhouse effect and contributing to global warming. Over time, the climate began to change, transitioning into ice ages when vast ice sheets covered significant parts of North America and Europe. These glaciers had a profound impact on sea levels, which dropped by tens of meters, opening up new lands and altering ecosystems. Over the past 2 million years, Earth has experienced at least 8 ice ages and interglacial periods, known as interglacials. During each of these periods, there were significant changes in the distribution of flora and fauna, creating conditions for the evolution of new species. For example, during ice ages, Neanderthals and other early humans adapted to cold climates by using fire and shelters, while in interglacials, their descendants developed more complex technologies and social structures. The increase in temperature during interglacials could reach up to 10 degrees Celsius over several thousand years, allowing forests to expand northward and deserts to shrink. Scientific research shows that such climate changes did not occur linearly, but as a result of complex interactions between different factors. For example, a study by a group of scientists led by Dr. John Murphy of the University of California showed that changes in Earth's orbit around the Sun played a key role in determining the duration and intensity of ice ages. Moreover, each time the climate shifted to a new state, there were abrupt changes in ecosystems, which in turn affected human societies. Data from paleoclimatic research show that even small temperature fluctuations could lead to mass population migrations, changes in agricultural methods, and even the collapse of civilizations. For example, in Mesopotamia, climate changes associated with droughts led to the fall of the Akkadian Empire around 2,000 years before our era. This variability in climate demonstrates the fragility of ecosystems and humanity's dependence on natural conditions. The climate of Earth is not a static system, but a dynamic phenomenon that is constantly changing, presenting both challenges and opportunities for living beings. Scientific data show that over the past 50 years, the average temperature on the planet has risen by 1 degree Celsius compared to pre-industrial levels, raising concerns about the future climate situation. The Paleocene-Eocene thermal maximum occurred approximately 56 million years ago and was one of the most significant climatic events in Earth's history. During this period, the temperature on the surface of the oceans rose by 5 to 8 degrees Celsius, leading to substantial changes in ecosystems. The increase in temperatures resulted in a significant decrease in the oxygen content of the water, which had a devastating impact on marine flora and fauna. For example, corals, which depend on a specific temperature regime and oxygen level, began to die en masse, leading to the destruction of coral reefs. This, in turn, reduced the diversity of marine inhabitants, as reefs served as habitats for thousands of fish and other organisms. On land, changes in climate led to shifts in the distribution of vegetation. Tropical forests began to expand into higher latitudes, while Arctic regions became warmer, allowing some plant species, previously not found in these areas, to begin growing there. At this time, the first examples of modern mammals, such as primates and the ancestors of modern elephants, began to actively evolve in response to changes in their environment. Research shows that for some groups of organisms, such as lizards and snakes, the warming became a stimulus for migration to the north and changes in their way of life, reflecting their adaptive abilities. Paleobotanists note that during this time, there was a rapid development of flowering plants, which began to displace more primitive spore-bearing plants such as ferns. This change in the plant cover led to the formation of new ecosystems that became homes for numerous species of insects, birds, and mammals. Notably, at this time, the concentration of carbon dioxide in the atmosphere also increased, contributing to the greenhouse effect and further warming. As a result, the Paleocene-Eocene thermal maximum became a key moment in the evolution of life on Earth, setting the direction for the subsequent development of both terrestrial and marine ecosystems. Specialists note that this event could have been caused by several factors, including volcanic activity and the release of methane from oceanic sediments, which is confirmed by geological data obtained from studies of deposits in regions such as North America and Europe. Scientific research shows that such rapid climate changes can be indicators of future ecological catastrophes if humanity does not take measures to reduce greenhouse gas emissions. The overall picture of the Paleocene-Eocene thermal maximum demonstrates how climatic changes can influence life on Earth, leading to massive migrations, extinctions, and evolutionary changes in ecosystems. The Paleocene-Eocene thermal maximum, which occurred approximately between 60 and 52 million years ago, was one of the most significant climatic events in Earth's history. The main cause of this phenomenon was the massive release of methane from methane hydrates located on the ocean floor. These methane hydrates are crystalline structures composed of water and methane, which form under high pressure and low temperature conditions, typical of deep sea zones. As global temperatures increased, driven in part by the rise in atmospheric carbon dioxide concentrations, methane hydrates began to decompose, releasing substantial amounts of methane. Estimates suggest that methane emissions could reach 4 to 6 million tons per year. This created a feedback loop. Initial warming facilitated the additional release of greenhouse gases, which in turn intensified global warming. As a result, Earth's temperature rose by approximately 5 to 6 degrees Celsius over a short period of several thousand years. During this time, not only did the climate change rapidly, but ecosystems also underwent significant transformations. For instance, the increase in ocean water temperature led to oxygen depletion, which negatively impacted marine life. While some species could adapt, many others could not survive in the new conditions, leading to mass extinctions. Concurrently, climate change also affected terrestrial ecosystems. Forests shifted towards the poles, and deserts expanded. Such changes were not only due to methane, but also to other factors, such as volcanic activity, which also released carbon dioxide and other greenhouse gases. Volcanoes active in the area of present-day Western Caucasus could emit millions of tons of carbon dioxide, further exacerbating the situation. Scientific research shows that such climatic changes have occurred over millions of years, and the Paleocene-Eocene thermal maximum is a vivid example of how the interaction of various natural processes can lead to abrupt and destructive fluctuations in the climate system. Around 30% of the methane released during this period could have originated from the oceans. This not only underscores the importance of methane hydrates as a significant climatic factor, but also reminds us of how fragile Earth's climate system is and how easily it can be destabilized. Scientists continue to study this period to better understand the mechanisms behind such changes and how they might be linked to current climate challenges. Approximately 2 million years before the onset of this maximum, changes in Earth's orbit occurred, which could also have influenced the climate. These changes, known as Milankovitch cycles, can cause fluctuations in the amount of solar radiation reaching Earth, which in turn can initiate further temperature changes. It was during this time that some of the most famous geological formations, such as the Alps and the Himalayas, were formed, and they continue to influence the climatic conditions in their respective regions. Hypothetical periods known as snowball Earth scenarios involve situations where glaciers covered almost the entire surface of the planet, including equatorial regions. Such phenomena could have occurred several times throughout Earth's history, especially during the Neoproterozoic era around 800 million years ago. At that time, the planet's temperature dropped so significantly that oceans froze at considerable latitudes, reaching almost to the equator. Under such conditions, photosynthesis virtually ceased, as sunlight could not penetrate through the ice and snow clouds. Life during this period existed only in refuges such as hot springs and deep-sea hydrothermal vents, where water temperatures could reach up to 100 degrees Celsius. One of the most famous examples is the hydrothermal vents on the ocean floor, which supported ecosystems based on chemosynthetic bacteria. These bacteria converted chemical energy released from minerals into food for other organisms, such as tube worms and various crustaceans. Due to the extreme conditions, inhabitants of such places had unique adaptations. For instance, tube worms used symbiotic bacteria to survive in conditions where ordinary food sources were unavailable. Meanwhile, on the surface, there was an icy wasteland. But beneath the ice, there could be small ecosystems where life continued to exist. In such refuges, there could also be shelf seas, where underwater volcanoes heated the water, creating more favorable conditions for living organisms. Some scientists, such as Peter D. S. Larson, suggest that such conditions could have led to significant changes in the biosphere, including mass extinctions, when organisms that were not adapted to the harsh conditions simply disappeared. This time also laid the groundwork for the evolution of new species as the climate began to change and glaciers retreated. As a result, when temperatures began to rise and conditions became more favorable, new life could colonize the newly available ecosystems. For example, During the Cambrian period, which began around 500 million years ago, there was a so-called Cambrian explosion, when the diversity of life on the planet increased dramatically. This process was possible because Earth had passed through extreme climatic conditions that acted as a catalyst for evolutionary changes. Such scenarios demonstrate how climatic catastrophes can rewrite the rules of existence on the planet, creating new niches for survival and adaptation. There are also geological data confirming the existence of ice caps in equatorial regions, such as the discovery of moraine deposits in equatorial region zones, which indicate the presence of glaciers in places where today there is a tropical climate. These discoveries underscore that Earth has gone through cycles of glaciation that have had a significant impact on the climate and life on the planet. During the transition out of the snowball Earth state, volcanic eruptions play a crucial role by releasing greenhouse gases such as carbon dioxide and methane into the atmosphere. These gases, emitted as a result of volcanic activity, accumulate in the atmosphere, creating a greenhouse effect. For instance, during the eruption of the Toba volcano in Indonesia approximately 78,000 years ago, volcanic gas emissions led to global cooling. However, in the subsequent millennia, as volcanic activity decreased, the concentration of carbon dioxide began to slowly increase. The rise in greenhouse gas concentrations in the atmosphere intensifies the greenhouse effect, contributing to global temperature increases. When temperatures reach critical levels, rapid melting of glaciers and polar ice begins, as evidenced by research from NASA scientists showing that Arctic ice volume has decreased by more than 68% over the past 40 years. This melting leads to rising sea levels and further deterioration of climate conditions. As a result, cycles of melting and freezing become more intense. For example, during the period between the 10th and 12th millennia BCE, the melting of glaciers caused sea levels to rise by 16 meters over just a few centuries. This process leads to significant changes in ecosystems, including species migration and biomes shifts. Meanwhile, the increasing concentration of greenhouse gases leads to a feedback loop. Higher temperatures cause even more methane to be released from permafrost, creating a vicious cycle. It is important to note that these processes do not occur linearly. They act as catalysts, driving transitions from one extreme to another. For example, a temperature change of just 1 degree can have catastrophic consequences for ecosystems, as illustrated by events at the end of the last ice age when rapid warming led to the extinction of many species such as mammoths and woolly rhinos. Scientific research shows that such rapid climate changes have occurred many times in the past, each leaving deep imprints on the biosphere. Ultimately, frozen lands transform into warm tropical zones, where conditions for life become much more favorable. However, this also presents new challenges for existing ecosystems. Over the past 40,000 years, such transitions have occurred several times, each time bringing significant changes to life on the planet. Mass extinction of animals and plants in the Anthropocene has become one of the most severe ecological catastrophes in Earth's history. According to researchers, the rate of species disappearance in our era reaches 100 species per day, which is tens to hundreds of times higher than the natural background level of extinction, which is 1 species per million per year. This phenomenon is linked to numerous factors, but the main one is human activity. Intensive urbanization, land use changes, environmental pollution, and climate change all contribute to the destruction of natural habitats. For instance, according to the World Wildlife Fund, more than 70% of ecosystems on the planet have been significantly altered due to human activity. Additionally, agriculture, which consumes around 70% of fresh water, also contributes to the loss of biodiversity, as it requires large areas for cultivation, leading to the destruction of natural landscapes. 80% of tropical forests, which serve as homes for many species, have already been cleared or severely damaged. One of the most worrying trends is that we are not only witnessing the disappearance of individual species, but entire ecosystems, such as coral reefs, which are suffering from ocean temperature increases and water acidification. Studies show that corals are losing their color due to stress caused by climate change and may disappear completely in the next few decades. An important aspect of the problem is that the extinction of species does not only affect individual organisms, but also entire ecosystems, disrupting food chains and interactions between species. Moreover, unlike previous mass extinctions caused by natural disasters, the current extinction has a clear human nature. Scientific research shows that if no immediate action is taken, by the end of the 21st century, up to 50% of all known species may disappear. Comparison with the past shows that previous mass extinctions took place over millions of years, while the current one is happening in just a few decades. This is a unique situation where one species, humans, is causing a global ecological transformation, threatening the existence of other species and the planet itself. In recent years, scientists have increasingly raised questions about how we can change our habits and interaction with nature to slow down this process. Scientific research conducted in the 21st century emphasizes the need for sustainable development and the preservation of biodiversity to prevent further losses. It is important to note that, unlike previous extinctions where some species survived, the current threats have a global scale, and without active actions, we risk destroying ecosystems that provide us with food, water, and air. As a result, according to ecologists, humanity is at a crossroads, where it is necessary to rethink its relationship with nature to avoid a catastrophe. Climate change, caused by an increase in carbon dioxide in the atmosphere, is already leading to changes in the living conditions of many species, further exacerbating the situation. In particular, the number of studies showing that more than 30% of all terrestrial mammals and birds are at risk of extinction is growing. Examples of such studies include those conducted by the International Union for Conservation of Nature, which updates the red list of species at risk of extinction every few years. It is important to understand that each species extinction has long-term consequences for ecosystems, as it can lead to disruptions in food chains and the deterioration of ecosystem health. For example, the disappearance of pollinators like bees can threaten the production of food for millions of people. Such facts highlight that we are not just witnessing the disappearance of species, we are witnessing the transformation of nature itself, where humanity plays not only the role of an observer, but also the main culprit. In Australia during the Holocene, a mass extinction of megafauna occurred, which began approximately 15,000 years ago when the first humans arrived on the continent. These early humans, known as Aborigines, became new predators for the Australian fauna that had evolved in isolation over millions of years. For a long time, the continent remained distant from other lands, leading to unique biodiversity where giant marsupials such as Megatherium and Diprotodon dominated among herbivores. For example, Diprotodon, the largest marsupial, reached the size of modern rhinos and weighed up to 2,000 kilograms. At the same time, giant birds like Genyornis, which could weigh up to 500 kilograms, also inhabited this continent. With the arrival of humans, hunting pressure on these species began, which they could not withstand. The extinction of large herbivorous animals led to significant changes in the ecosystems of Australia. Without the control of large herbivores, vegetation began to develop in a different direction. For example, there was an increase in the number of shrubs and grasses, which affected fire regimes. The increase in vegetation in turn created conditions for more frequent and intense fires, which became catastrophic for the ecosystem. Fires that in the past could be controlled by large herbivores now posed a real threat to the survival of the remaining species. As a result of these changes, many small species began to lose their usual habitats. Research shows that the extinction of megafauna also changed the structure of the soil and its ability to retain moisture. The disappearance of large animals like Diprotodon disrupted processes related to seed dispersal, as these giants contributed to maintaining biodiversity through their habits of eating and moving. Without these processes, the ecosystem of Australia became more uniform and vulnerable to climate changes. Scientific research conducted by scientists such as Dr. Kenneth McNeil shows that climate change in combination with human activity exacerbated the situation. For example, fluctuations in temperature and rainfall levels added additional stresses to the ecosystem, which ultimately contributed to the extinction of the remaining species. Thus, human intervention in the ecosystem of Australia led to irreversible consequences that are still felt today. As a result, Australia lost more than 40 species of large mammals, making it one of the most significant extinctions in the history of the planet. On the island of Mauritius, discovered by Europeans in 1598, there lived a unique species, the dodo, or dronte, which could not fly and reached a height of about 1 metre. This flightless pigeon, weighing up to 25 kilograms, became a symbol of the tragic extinction of species due to human activity. When the Portuguese and later the Dutch began exploring the island, the dodo was unaware of the threats that lay ahead. Initially, it was caught for its meat, as the bird was an easy prey and unable to escape predators. By the 1610s, when the Dutch began actively hunting the dodo, its population began to decline rapidly. At the same time, pigs, rats, and monkeys were introduced to the island, which began to eat the dodo's eggs, thus destroying its reproductive potential. Within just a few decades, by 1631, the last observed dodo was recorded. Despite the efforts of researchers to preserve this species, the dodo disappeared forever in less than a century from the discovery of the island. The problem lay not only in the dodo's lack of self-preservation instincts, but also in the tragic misunderstanding by colonizers of the value of this unique species. The dodo could not adapt to the new conditions created by human activity. The 18th century was a time of complete devastation, when the dodo disappeared, leaving behind only memories and museum exhibits. Research conducted in recent decades shows that the dodo was not just an unusual creature, but also an important part of Mauritius's ecosystem, playing a role in the dispersal of seeds of local plants. Thus, the extinction of the dodo became not only an ecological catastrophe, but also a clear example of human recklessness, which did not understand that each species' extinction had irreversible consequences for the environment. Unfortunately, by 1633, the dodo had become completely extinct, leaving behind only traces in the annals of history. Modern methods of preserving endangered species include various strategies aimed at preventing new extinctions and maintaining biodiversity on the planet. One of the most well-known approaches is captive breeding, which is actively used to restore populations of species such as the black rhino and the Amur tiger. In the year 2000, a large-scale project to breed black rhinos was successfully launched at the San Diego Zoo, increasing their population from fewer than 100 individuals to more than 400 by 2021. The program employs complex methods of selection and genetic monitoring, which enhance the chances of successfully restoring populations in the wild. Genetic material conservation also plays a significant role in modern efforts to preserve species. For example, in 2008, the Wildlife Conservation Society began a project to freeze sperm and egg cells of endangered species such as the Javan rhino and the grey vulture. These frozen samples can be used in the future to create new individuals and restore genetic diversity. Restoring ecosystems is another important strategy that involves not only protecting endangered species, but also restoring their natural habitats. In 2006, the Taranaki Ecosystem Reconstruction Project was launched in New Zealand, with the goal of restoring local plant and animal species affected by agriculture and urbanisation. Scientists and conservation organisations are working to restore populations of local birds and insects through planting native plants and creating protected areas. For instance, in 2009, over 8,000 native trees and shrubs were planted in this project, helping to restore the natural habitat for many local fauna species. A key aspect of this work is the involvement of local communities, who are engaged in the process of nature conservation and ecosystem restoration, thereby increasing the chances of successfully preserving biodiversity. Support for such initiatives from governments and international organisations, such as the World Wildlife Fund, WWF, also plays a crucial role in these efforts. In 2003, WWF launched a global biodiversity conservation program that includes funding for ecosystem restoration projects in various regions of the world. For example, in Africa, projects to restore forests are being implemented, which not only help to conserve endangered species, but also maintain the health of ecosystems. The success of these programs depends on many factors, including scientific research, funding, and the involvement of local communities, making the issues of nature conservation complex and multifaceted. It is important to note that to date, more than 150 species of animals and plants have been successfully removed from the critically endangered status due to such measures. Anthropogenic climate change is a complex and multifaceted process that affects all aspects of our planet. This phenomenon is driven by the increase in the concentration of greenhouse gases, such as carbon dioxide, methane, and nitrous oxides in the atmosphere. According to the World Meteorological Organization, the level of carbon dioxide in the atmosphere has risen by more than 30% over the past decades compared to pre-industrial levels. This increase is a result of human activities, burning fossil fuels, deforestation, and agricultural production. The increase in the concentration of carbon dioxide and other greenhouse gases intensifies the greenhouse effect, where sunlight penetrates the Earth's surface, but the heat reflected back from the surface cannot fully escape the atmosphere. This leads to an increase in the average global temperature. For instance, since the beginning of the 20th century, global temperature has risen by 1 degree Celsius, which has already caused significant changes in climate systems. These changes are not limited to temperature increases, but also include changes in precipitation, sea level rise, and an increase in the frequency of extreme weather events such as hurricanes and droughts. These processes exacerbate existing ecological problems, creating a vicious cycle where climate change affects ecosystems, and these, in turn, influence the climate. As a result, anthropogenic factors accelerate natural climate processes, such as the melting of glaciers and changes in ocean currents. For example, according to scientists from NASA, the Arctic is losing ice faster than expected, which further accelerates warming in the region and affects global climate systems. Increased temperature leads to higher evaporation rates, causing more intense rainfall in some regions and droughts in others. This imbalance in water distribution negatively impacts agriculture, ecosystems, and water supply. From an ecological perspective, anthropogenic climate change poses a threat to the existence of many animal and plant species, as they cannot adapt quickly enough to the rapidly changing conditions. For example, coral reefs, already suffering from rising temperatures and ocean acidification, are experiencing significant stress and may die in large numbers. The increase in greenhouse gas concentrations creates a situation where the planet's climate system can no longer remain in balance, and the consequences of this will be felt for decades and even centuries. Therefore, anthropogenic climate change has become one of the most serious threats to the future of humanity and the planet as a whole. According to experts, if current trends continue, this will lead to significant changes in ecosystems, the economy, and human well-being. The melting of Arctic ice is happening at an alarming rate, and its consequences are already apparent. According to NASA, since the year 2000, the area of sea ice in the Arctic Ocean has decreased by approximately 30%, and the average thickness of the ice has halved. The white surface of the ice, which reflects solar radiation, is being replaced by dark water, which absorbs heat. This process creates a positive feedback loop. The less ice there is, the more heat the ocean absorbs, which in turn leads to further melting of the ice. Scientists from the Woods Hole Oceanographic Institute in the United States note that this phenomenon significantly accelerates warming in the Arctic, where the air temperature is rising twice as fast as in other regions of the planet. As a result of climate change, not only are the ecosystems of the region suffering, but also indigenous peoples such as the Inuit and the Nensi, who depend on the ice cover for hunting and fishing. These peoples are facing changes in animal migration patterns and a decrease in populations of species such as polar bears and seals, which threatens their traditional way of life. For example, polar bears, which rely on ice for hunting seals, are forced to travel longer distances in search of food, leading to a decline in their population. Studies show that the polar bear population in some areas has decreased by 30% over the past 2 decades. Concurrently, climate change is causing concern among local residents about the safety of their communities, as the melting of permafrost is leading to the destruction of infrastructure, including homes and roads. As a result, the indigenous peoples of the Arctic are facing the need to adapt to new conditions, which requires significant efforts and resources. However, adapting to changing conditions is an extremely challenging task, as traditional knowledge and practices are not always applicable in conditions where the ecosystem is rapidly changing. In some cases, indigenous communities are beginning to use new technologies and methods to cope with the consequences of warming, but many of them face a shortage of resources and support. It is important to note that the melting of Arctic ice also affects global climate systems, as it can lead to changes in ocean currents and weather patterns around the world. For example, the reduction in ice can alter the direction of the Gulf Stream, which in turn can affect the climate in Europe and North America. According to the UK Meteorological Service, such changes are already being observed, and they could lead to colder winters in some regions and more frequent extreme weather events. The reduction in the area and thickness of the ice cover in the Arctic is not just a local problem, but a global challenge that requires attention and action at the international level. Projections show that by the 2060s, summer ice in the Arctic could disappear completely, leading to even more serious consequences for ecosystems and the climate as a whole. Glaciers in Greenland and Antarctica continue to lose stability, and this trend is becoming increasingly evident. Greenland, with its ice sheet covering around 1 million square kilometers, loses ice at an average rate of 300 billion tons per year. This leads to a global sea level rise of approximately 1 millimeter annually. NASA research conducted in 2017 showed that the rate of glacier retreat has doubled over the past 30 years. The situation in Antarctica is no less alarming. The ice sheet covering the continent loses between 300 and 400 billion tons of ice per year, contributing to a sea level rise of several millimeters. One of the most vulnerable areas is West Antarctica, where glaciers such as the Thwaites Glacier are moving faster due to the melting of underwater ice platforms. By the year 2000, its speed of retreat was around 30 meters per year, and by 2020, this speed had increased to 100 meters per year. This is due to warm ocean waters penetrating beneath the ice sheets and eroding them from below, making them even more susceptible to collapse. As a result of this process, massive icebergs are formed, which break off from the glaciers and enter the ocean. In 2018, an iceberg the size of Delaware, known as a 68, broke off from the Larsen C ice shelf and became one of the largest in history. Its area was approximately 5,000 square kilometers, and it became a symbol of global warming. Additionally, according to scientists from the University of California, Irvine, in the 2020s, the number of unstable glaciers is increasing, which could lead to even larger icebergs. This process has not only local, but also global consequences, affecting ocean currents and ecosystems. For example, the melting of glaciers alters the salinity and temperature of ocean waters, which in turn can impact climate conditions in distant regions such as Europe and North America. Glaciers not only serve as water bodies, but also play a crucial role in maintaining the global sea level. Any changes in their state can have catastrophic consequences for coastal cities and island nations. By the 2080s, sea levels are projected to rise by 1 meter or more, flooding significant areas and causing mass population displacement. In this context, the melting of glaciers represents a slow but inexorable process that is reshaping our planet, threatening the stability of ecosystems and human life. Rising sea levels are the result of the complex interaction of factors such as glacier melting and thermal expansion of water, leading to the gradual submersion of low-lying coastal areas. According to the Intergovernmental Panel on Climate Change, by the 2030s, sea levels could rise by 80 centimeters, and by the 2080s, they could rise by 1 meter or more. This threatens coastal cities like Mumbai, Bangkok, and New York, where millions of people live in low-lying areas. For instance, Bangkok, located only 1 to 2 meters above sea level, experiences flooding even under normal conditions due to both sea level rise and excessive groundwater extraction, which causes land subsidence. Studies indicate that by the 2050s, up to 30 million people worldwide could be displaced by flooding, leading to mass migration. Island nations like the Maldives and Tuvalu are already on the brink of disappearing. To adapt infrastructure, comprehensive solutions such as building protective dikes, creating drainage systems, and raising the height of new buildings are needed. Some countries, like the Netherlands, have successfully implemented technologies to control water levels. But this requires significant financial investment and political will. the need for relocating populations from flooded areas is becoming increasingly urgent. In some cases, such as the village of Niihau in Hawaii, residents have begun discussing the possibility of moving to safer territories. Rising sea levels are not only an environmental, but also a social problem, requiring immediate action and a comprehensive approach to resource management. By the 2020s, it is estimated that more than 20 major cities worldwide could be at risk of flooding, necessitating the development of new adaptation and migration strategies. Changes in precipitation patterns due to global warming are becoming increasingly noticeable and have serious consequences for ecosystems and human activities. According to the World Meteorological Organization, the number of extreme weather events, such as droughts and floods, is increasing, leading to unpredictable conditions that traditional farming methods cannot handle. For instance, in Eastern Africa, where one of the strongest cyclones was observed in 2020, more than 7 million people faced food shortages due to the combination of floods and droughts. Meanwhile, in California, where the average rainfall has fluctuated in recent decades, record levels of drought were recorded in 2020, prompting local authorities to impose strict water use restrictions. In some regions of Afghanistan, where rain was traditionally abundant, a sharp decrease in rainfall was observed in 2020, leading to increased agricultural crop failures and food insecurity. The intensification of rainfall in other regions, such as South America, causes floods that not only inundate fields but also cities, threatening infrastructure and public health. A study conducted by Columbia University in 2020 found that more than 50 million people worldwide have become victims of climate-related natural disasters. As a result of frequent floods in Bangladesh, tens of thousands of homes are lost, and local residents are forced to relocate, leaving their fields and livelihoods behind. The problem is exacerbated by the increasing unpredictability of precipitation patterns. In some regions, rains come with incredible force, while in others, they are completely absent. In Europe in 2020, a sharp increase in flooding was observed in Germany and Belgium, while in Greece and Spain, historical drought levels were recorded. Such a contrast in weather conditions forces farmers to adapt to new realities, but traditional methods often fail to work. Research shows that with climate change, agronomists must reassess their strategies as traditional crops become vulnerable. For example, in India, where rural populations heavily depend on seasonal rains, agronomists have begun experimenting with new crop varieties that can withstand both drought and excessive water. The effectiveness of such approaches remains uncertain, as transitioning to new methods requires time and resources. According to the United Nations, by 2030, more than 100 million people may become victims of climate change if immediate measures are not taken. Ultimately, changes in precipitation patterns lead to increasing unpredictability of weather conditions, threatening both agriculture and urban infrastructure. In some countries, such as Mexico, governments are already developing new strategies for managing water resources to address this challenge. Geoengineering is a concept that involves deliberate human intervention in Earth's climate system to mitigate the effects of global warming. Historically, the idea of actively influencing natural processes is not new. Scientists began discussing the possibility of climate control in the mid-20th century. But modern geoengineering has only become a subject of intense research and debate in the last 2 decades. According to the Intergovernmental Panel on Climate Change, the planet's temperature has already risen by 1 degree Celsius compared to pre-industrial levels. This has led to the melting of glaciers, rising sea levels, and the intensification of extreme weather events such as hurricanes and droughts. Scientists warn that if no decisive action is taken, by the 2060s, the temperature could rise by 2 to 3 degrees, which would be catastrophic for ecosystems and human life. Geoengineers propose various approaches to address this problem, including methods that could reduce the amount of sunlight reaching Earth or increase the absorption of carbon dioxide by oceans and land. However, these methods raise numerous questions and concerns. Interfering with the climate system could lead to unpredictable consequences that affect ecosystems and climate conditions, potentially causing new problems such as changes in precipitation patterns or the destruction of natural habitats. The unpredictability of these consequences raises serious ethical and scientific questions. For example, who would be responsible for any negative consequences? What impact could these changes have on different regions of the planet, especially those already experiencing climate crises? Research shows that some countries might benefit from geoengineering projects, while others could face serious problems such as water scarcity or deterioration of agricultural conditions. This complex ethical choice between the risks of inaction and the risks of active intervention in the climate system requires carefully considered solutions and global cooperation. It is important to understand that geoengineering is not a panacea, and any intervention must be thoroughly planned and justified. In the 21st century, as humanity faces the consequences of its impact on nature, the question of how to manage the climate has become not only a scientific, but also a social and political challenge. Research indicates that the likelihood of severe climate catastrophes will increase if no action is taken. Spraying aerosols in the stratosphere is a technology aimed at reducing global temperature by reflecting solar radiation, mimicking the effect of volcanic eruptions. Volcanic eruptions, such as the Pinatubo eruption in the Philippines in 1999, demonstrated how sulfur emissions into the atmosphere can temporarily lower the average global temperature by several degrees. The most common aerosol for such manipulations is sulfate, which can be delivered to the stratosphere using high-altitude aircraft such as the Global Hawk, capable of reaching heights of over 20 kilometers. Furthermore, there are projects proposing the use of airships or even rockets for aerosol transport. For instance, in 2000, scientists proposed using specialized drone technologies for aerosol spraying, which would allow for more precise control of the process and minimize risks. However, such technology is not without side effects. One potential consequence is the alteration of precipitation. Studies show that increasing the content of aerosols in the atmosphere can lead to an uneven distribution of precipitation, resulting in droughts in some regions and floods in others. Additionally, sulfates can affect the ozone layer, which protects Earth from harmful ultraviolet radiation. Modeling conducted in 2015 showed that aerosol spraying could reduce the level of ozone in the stratosphere by 10% in some areas. Research also indicates the possibility of a feedback effect, where climate changes can be exacerbated by artificial intervention. It is important to remember that, despite the potential benefits, such technologies require careful evaluation and monitoring to avoid unforeseen consequences. For example, in 2019, scientists from the Massachusetts Institute of Technology proposed a method involving the spraying of aerosols using unmanned aerial vehicles, but emphasized the need for the creation of international norms and standards for controlling the use of such technologies. Aerosols in the stratosphere can remain active for several years, meaning their impact on climate can be long-lasting and complex to predict. Technologies for capturing and storing carbon represent a complex and large-scale challenge, requiring the creation of extensive infrastructure comparable in size to the oil industry. Direct capture of carbon dioxide from the atmosphere is achieved using technologies such as direct air capture, DAC. For example, in 2020, the company Climeworks launched the Orca plant in Iceland, which can capture up to 400 tons of CO2 per year. This process involves the use of a special sorbent that absorbs CO2 from the air, after which the gas is heated to separate it. However, this is just the beginning. Captured CO2 must not only be stored, but also effectively bound and returned to the Earth to prevent its re-entry into the atmosphere. For this, technologies such as mineralization are used, where carbon is bound to minerals, forming stable compounds that can be stored for thousands of years. In 2020, an experiment was conducted on Hawaii, where researchers were able to demonstrate the process of binding carbon with volcanic rock, which ultimately led to the formation of minerals containing CO2. Creating such infrastructure requires significant capital investment and long-term planning, as the scale of work will exceed current efforts in coal and oil mining. Assessments show that to achieve the goal of reducing the level of carbon in the atmosphere, it is necessary to capture more than 1 trillion tons of CO2 by 2030. This implies the construction of thousands of CO2 capture plants, which should be distributed around the world, especially in industrial centers and near sources of carbon, such as power plants and factories. At the same time, a network for transporting and storing carbon must be created, which will require the development of new technologies and methods, such as underground storage in geological formations. For example, in 2015, Norway launched the Snøhvit program, which includes capturing CO2 from a gas processing plant and transporting it to a depth of more than 1,000 meters below the seabed, where it is subsequently stored in old gas fields. The problem lies not only in technical aspects, but also in creating an economic model that makes carbon capture profitable. For example, in 2020, some researchers proposed using carbon credits to create financial incentives for companies involved in CO2 capture. However, this would require international cooperation and strict regulation to prevent manipulation in the carbon credit market. It is also important to consider that the effectiveness of carbon capture technologies depends on the level of CO2 concentration in the atmosphere. And in this context, the transition to cleaner energy sources and reducing emissions is a crucial aspect. Despite all the challenges, technologies for capturing and storing carbon can become a key element in the fight against global warming if they are implemented at the required level. Research in 2020 showed that each DAC plant can reduce the level of CO2 in the atmosphere by tens of thousands of tons per year if their production is scaled up. Healthy ecosystems such as forests, wetlands, and marine ecosystems play a crucial role in carbon sequestration and providing numerous ecological services. For instance, forests can absorb carbon dioxide through photosynthesis, with 1 hectare of mature tropical forest capable of storing up to 200 tons of carbon. A study conducted by scientists from the University of Grenoble in 2009 showed that reforestation could reduce atmospheric CO2 levels by more than 3 billion tons per year, equivalent to the annual carbon emissions from 7 billion cars. Wetlands also have immense significance. These ecosystems can retain carbon in the form of peat and can absorb up to 30 tons of carbon per hectare per year, while also preventing flooding and improving water quality. Research conducted in California in 2006 showed that restoring 1 hectare of wetland can absorb up to 30,000 tons of CO2 over the entire lifespan of the wetland, which can be more than 100 years. Marine ecosystems, such as mangrove forests and seagrasses, also serve as important carbon sinks. A study published in the journal Nature Climate Change in 2019 found that mangrove forests can accumulate carbon 3 times faster than tropical forests. Moreover, they protect coastlines from erosion and provide habitats for numerous species. Restoring and protecting healthy ecosystems not only helps reduce carbon levels, but also preserves biodiversity, providing habitats for many animals and plants. In 2018, the World Wildlife Fund, WWF, reported that nearly 30% of all known animal species depend on ecosystems that are at risk of disappearing. Protecting and restoring such ecosystems also helps regulate water regimes, reducing the risk of floods and droughts. For example, research shows that restoring wetlands in Southeast Asia has led to a reduction in flooding by more than 30% in some regions. Therefore, healthy ecosystems are not only important carbon sinks, but also indispensable for maintaining ecological balance on the planet. Throughout the history of Earth, the planet has encountered various celestial objects, and this process continues to this day. In the Earth's vicinity, there are thousands of objects, including asteroids and comets, moving along orbits that intersect with our planet's path. Asteroids can range in size from small pebbles to giants with diameters of several kilometers. Each year, Earth encounters thousands of micrometeoroids that burn up in the atmosphere, creating meteors, but much larger objects pose a significant threat. For instance, according to NASA data, approximately 90% of objects larger than 100 meters have been detected. But this represents only a small fraction of the total number of potentially hazardous asteroids. Estimates suggest that there could be up to 1 million objects ranging from 1 to 100 meters in size in the Earth's vicinity, periodically crossing the planet's orbit. These objects move at tremendous speeds, reaching up to 100,000 kilometers per hour, making a collision with them catastrophic for our planet. Historically, such events have led to massive devastation, such as the asteroid that, according to geological data, caused the mass extinction of dinosaurs around 66 million years ago. While many of these objects remain undetected, their impact on our planet is incalculable. Additionally, there are specialized programs aimed at tracking and studying these objects, such as NASA's Near-Earth Object Observations, NEOO, which analyze data on potentially hazardous asteroids daily. However, not all asteroids are classified as dangerous, and many simply pass by Earth without posing a threat. Nevertheless, the likelihood that one of these objects could ultimately affect Earth remains real. Astronomers continue to study the dynamics of these objects to prevent potential consequences of their collisions with our planet. For example, some researchers estimate that the probability of a collision with an object 1 kilometer in diameter within the next century is approximately 1 in 8,000. This prompts us to consider the necessity of protecting against such threats. Scientific research shows that even small changes in the orbits of asteroids can have significant consequences if they occur at critical moments. It is important to note that many countries, starting with the United States and including Russia and the European Union, are actively involved in international efforts to monitor and study these objects. They use various technologies, including telescopes and spacecraft, to track the movement of asteroids and predict their orbits. For example, NASA's DART mission, scheduled for 2021, aims to test the feasibility of altering an asteroid's trajectory with a collision. This underscores that humanity is aware of the seriousness of the asteroid threat and is prepared to act. Meanwhile, our existence in space is not only filled with threats, but also with opportunities, as asteroids can contain valuable resources such as metals and water, which could be used in the future for the colonization of other planets. However, given the constant movement of Earth through space, surrounded by potential threats, it is important to remain vigilant and ready for any unexpected events. Every day, astronomers discover new objects, highlighting the dynamic nature of our environment. In the 21st century, interest in this topic is growing, and the number of missions to study asteroids will only increase. Scientific research indicates that in the coming decades, we can expect significant progress in the field of tracking and possibly even protecting against asteroid threats. Modern programs for detecting and cataloging near-Earth objects use a combination of high-tech telescopes, data processing algorithms, and international cooperation. Astronomers like Dr. Linda Spilker, a leading researcher in the Catalina Sky Survey program, use powerful telescopes, such as the 10-meter Subaru telescope in Hawaii, to scan the sky. These telescopes can capture a vast number of images, enabling the detection of moving objects like asteroids and comets. It is worth noting that in the 21st century, there has been a significant increase in such observations. From the early 2000s, the number of discovered near-Earth objects has grown from a few hundred to over 30,000. Complex algorithms are used to process the collected data, which can automatically recognize and track the movements of celestial bodies, calculating their orbits with an accuracy of several meters. These algorithms, such as those developed in the Pan-STARRS project, allow astronomers to quickly assess the potential danger of each discovered object. Once an object is identified, its orbit is modeled using data on its speed and trajectory, allowing for predictions of its future movement within a few years. The assessment of potential danger involves calculating the minimum possible distance at which the object could cross Earth's orbit. For example, the asteroid known as Apophis was initially assessed as a threat to Earth in 2009 when its orbit crossed ours. But further observations refined its trajectory, and now the threat is minimal. International cooperation plays a crucial role in these efforts, combining resources and data from different countries. Projects such as NEOWISE include satellites that make infrared observations, enabling the detection of darker and colder objects that are difficult to see from Earth. In the 21st century, global databases have been created, such as NASA's Near-Earth Object Program, which contains information on all registered near-Earth objects. These databases help astronomers and scientists in assessing risks and planning possible missions to deflect threatening objects. Regular data updates are crucial for tracking changes in orbits, which is essential for accurate predictions. 41% of all known near-Earth objects were discovered in the last 5 years, highlighting the necessity and relevance of current monitoring programs. In the past few decades, scientists have developed several concepts for protecting Earth from asteroid threats. which could significantly alter our understanding of humanity's capabilities in combating cosmic catastrophes. One of the most discussed technologies is the kinetic impactor. This method involves launching a spacecraft that collides with an asteroid at high speed, altering its trajectory. An example of this approach is the DART Double Asteroid Redirection Test mission, launched by NASA in November 2021. It is aimed at the binary asteroid system Didymos and Dimorphos, where the goal is to change the orbit of the smaller body, Dimorphos, using a collision. The impact is expected to occur in September 2022, and the results of this experiment will help assess the effectiveness of kinetic impactors in the future. The second approach is gravitational tractors, which involve using a spacecraft to create a gravitational field capable of slowly altering the orbit of an asteroid. This concept was primarily developed by scientists from MIT and other research institutions who proposed using large spacecraft, such as gravitational tractors, that could exert a prolonged influence on an asteroid, changing its trajectory through the effect of gravity. This method requires time but can be effective in altering the course of even large asteroids that pose a threat. Nuclear explosions are the third approach, which is highly controversial but offers the possibility of changing an asteroid's trajectory. This method involves detonating a nuclear device near the asteroid to create a powerful shockwave that changes its course. Research conducted under the Planet Earth program in the United States in the 1970s showed that if the parameters of the explosion are correctly calculated, this approach can be viable. However, the use of nuclear weapons in space requires strict adherence to international agreements, such as the Treaty on the Prohibition of Nuclear Explosions. Humanity is no longer a passive victim of cosmic threats. Programs for monitoring and developing technologies to protect against asteroids demonstrate that we can become active participants in shaping a safe near-Earth environment. For example, the European Space Agency, ESA, is launching the HERA project, which will monitor the aftermath of the DART impact and analyze the physical characteristics of the asteroid. This will help us not only protect our planet, but also understand how to utilize asteroid resources in the future. Scientific research conducted within these programs shows that even small changes in asteroid trajectories can prevent catastrophes, such as the mass extinction that occurred around 66 million years ago when an asteroid with a diameter of 10 kilometers collided with Earth, leading to the disappearance of the dinosaurs. It is important that modern science and technology allow us to develop methods that can act preemptively before the threat becomes critical. Kinetic impactors, gravitational tractors, and nuclear explosions are just some of the methods that can help protect our planet from inevitable cosmic threats. In this context, it becomes clear that future technologies will determine not only the safety of Earth, but also its future in space. For instance, in 2020, scientists successfully tested a system that uses lasers to change the trajectory of small asteroids. This technology could become an important addition to existing methods, providing humanity with a broader range of tools for protecting against threats from space. International cooperation in the field of planetary defense has become a crucial aspect in combating space threats, uniting the efforts of countries to coordinate observations, data exchange, and joint missions. In 2012, at a conference in Tokyo, representatives of more than 60 states agreed to establish the International Center for Coordination of Space Object Observations, marking a significant step towards the formation of a global monitoring network. This network allows tracking not only asteroids, but also comets that could pose a threat to Earth. Within the NASA project Near-Earth Object Observations, numerous observations were conducted, including those using telescopes located in different parts of the planet, ensuring a wide coverage and high accuracy of data. For example, in 2019, scientists detected more than 12,000 objects near Earth, enabling an assessment of the risk of collision with our planet. Data exchange plays a vital role in this process. Within the Space Situational Awareness Program, the European Space Agency, ESA, actively shares information about potentially dangerous objects with other countries, allowing for prompt responses to possible threats. In 2020, several agreements on joint research were signed between ESA and NASA, enabling the combination of resources and expertise for more effective asteroid studies. One of the most notable examples of such cooperation was the participation in the NASA mission DART, Double Asteroid Redirection Test, launched in 2020, aimed at testing methods for deflecting an asteroid. International partners, such as the Japanese Aerospace Exploration Agency, JAXA, also participated in this mission, underscoring the importance of joint efforts in addressing global problems. The threat from space is a powerful factor that drives countries to overcome political differences and unite for common security. In 2021, at a meeting in the UN, more than 100 countries signed a declaration on the necessity of joint actions to protect the planet from space threats, indicating a growing consensus among the global community. Such initiatives demonstrate that even in the face of tense international relations, states can find common ground when it comes to the survival of humanity. Participation in such projects requires not only resources, but also political will, emphasizing the importance of a global approach to solving this problem. There are also independent initiatives, such as the Planetary Defense Conference, where scientists and experts from different countries discuss strategies for responding to potential threats, fostering the exchange of knowledge and technologies. As a result of these efforts, awareness of risks and opportunities increases, influencing the development of new technologies for protection against space objects. In 2020, at a conference in Washington, a new early warning system for space threats was presented, developed jointly by scientists from the US and Russia, marking the first step towards creating a unified international platform for monitoring space objects. With each passing year, the number of countries interested in planetary defense continues to grow. Currently, more than 130 organizations worldwide are engaged in research in this area, highlighting the importance of the problem. Scientific research and international cooperation are the guarantee of safety for all Earth's inhabitants, as the threat can come from anywhere and at any time. In the future, over the course of tens of millions of years, the movement of tectonic plates will lead to the formation of a new supercontinent, which will be the result of complex geological processes actively taking place beneath our planet. Tectonic plates, which move at speeds ranging from several millimeters to several centimeters per year, gradually shift and collide with each other. This results in the formation of mountain ranges, such as the Himalayas, which arose from the collision of the Indian and Eurasian plates. According to the theory of continental drift, proposed by Alfred Wegener at the beginning of the 20th century, continents are not static but are in constant motion, which has already led to the formation of supercontinents such as Pangaea, which existed around 300 million years ago. Currently, as we observe the movement of plates, we can only speculate about how they will interact in the future. For example, the North American plate continues to move northwest, while the Australian plate moves north, which could ultimately lead to their collision. This interaction of plates not only creates new geographical formations, but also influences climate and ecosystems, as the change in the position of continents can significantly alter marine and atmospheric currents. Processes such as subduction, where one plate descends beneath another, and the spreading of plates, which create new oceanic floors, continue to shape our planet. Research shows that the processes occurring on Earth have a cyclic nature, and over billions of years, continents have continually changed their positions. Existing models predict that in the future, the continents will once again unite, forming a giant supercontinent, which will lead to a new distribution of the biosphere, ecosystems, and climate. For example, the merging of continents could result in a single ocean, altering the conditions for life on Earth. Looking at the history of geology, we see that such changes occur over millions of years, while human civilization is but a fleeting moment in the face of these processes. It is important to understand that the tectonic processes currently taking place on Earth will continue even after the disappearance of humanity, and continents will continue to move, forming new landscapes and ecosystems. From the perspective of timescales, the movement of plates is a constant and unyielding process, and it knows no end. Ultimately, over millions of years, a new supercontinent may form, which will become home to forms of life that we can barely imagine today. Scientific research shows that existing continents, such as Africa and Europe, continue to move towards each other at a rate of about 2 centimeters per year, which in the future could lead to the formation of new mountain ranges and changes in the geography of the continents. This endless movement will continue, regardless of whether we, humans, disappear. Data also show that tectonic activity influences volcanism and earthquakes, which in turn create new conditions for life. For example, volcanoes resulting from subduction can create new islands and ecosystems, while earthquakes can form new geographical features. It is important to understand that this process is not just a random occurrence, but the result of the interaction of forces that have been acting on the planet for millions of years. The model of the future supercontinent Pangaea Ultima suggests that approximately 250 million years from now, the continents will reunite into a single mass of land. Scientists such as Dr. Stephen Satterfield from the University of California have conducted research indicating that tectonic activity will continue, causing the current continents to migrate northeastward, forming a large landmass around the equator. This new Pangaea will have an almost circular shape, surrounded by an ocean, with its central part significantly elevated above sea level. As a result, a unique geography will emerge, where high mountain ranges will be located in the center of the supercontinent, while low-lying areas will be closer to the coasts. The internal regions will experience an extreme continental climate with high temperatures and low rainfall, leading to the formation of vast deserts. For example, in the central part of the supercontinent, conditions similar to those in the modern Gobi or Sahara deserts may arise, where the average annual temperature can reach 35 degrees Celsius. Along the coasts, where the influence of the ocean will be more pronounced, the climate will be milder, possibly featuring a warm, humid tropical climate. This will create a diversity of ecosystems, with tropical forests growing in coastal areas and arid steppes and deserts in the continental centers. Considering that tectonic processes occur slowly, this unification of continents will be the result of millions of years of plate movements, such as the movements of the Philippine and Pacific plates, which will contribute to the formation of new mountain ranges and faults. Research indicates that during this period, volcanic activity may increase, also affecting climate conditions by providing additional sources of heat and precipitation in certain regions. Existing oceans, such as the Atlantic and Pacific, will gradually shrink, while new ocean basins may form in the places of the old continents. Consequently, by the time Pangaea Ultima is formed, the world will look entirely different from today, and the natural balance of ecosystems will undergo significant changes. It is important to note that such changes require not only the movement of tectonic plates, but also other geological processes, such as erosion and sediment deposition, which will occur over millions of years. The predicted area of Pangaea Ultima will be around 100 million square kilometers, making it one of the largest supercontinents in Earth's history. On the hypothetical supercontinent Pangaea Ultima, the climate will drastically differ from the present one. The internal regions of this vast landmass will experience extreme seasonal temperature fluctuations, with summer heat potentially reaching 50 degrees Celsius and winter temperatures dropping to -30. These contrasts will be caused by the absence of oceanic currents that typically moderate the climate, and the enormous distances from the coasts to the interior regions, making them particularly vulnerable to arid conditions. In such conditions, a significant portion of the land, far from the oceans, will become unsuitable for complex life forms, leading to the extinction of many species. The percentage of arid territories may exceed 70% of the continent's total area, resulting in vast deserts with rare oases. In contrast, coastal regions will become centers of biological diversity, thanks to monsoon seasons that provide the necessary moisture and rainfall. Monsoons, driven by sharp temperature contrasts between the sea and land, can bring up to 2,000 millimeters of rainfall per year, making these areas ideal for plant and animal life. In such conditions, flora and fauna will concentrate in a narrow strip along the coastal line, where ecosystems will depend on regular rainfall and moderate temperatures. This will create a unique biocenosis, where species adapted to high humidity will coexist with those that can survive in arid conditions. Research indicates that on Earth, during periods when the climate was similar, such as in the late Paleozoic era, extensive tropical forests existed along the equator, while to the north and south of them lay drier and less fertile zones. Therefore, on Pangaea Ultima, where the climate will be drastically altered, biological diversity will be concentrated in these coastal monsoon zones, creating a contrast between desolate interior regions and exotic ecosystems along the oceans. An example of such a phenomenon can be seen in contemporary monsoon regions like Southeast Asia, where life conditions can differ significantly even over short distances. Over the course of millions of years, life on Earth has continually adapted to changing conditions. In the future, when humanity disappears, ecosystems and organisms are likely to undergo significant transformations. In the face of global warming and climate change, which are already occurring, some species may become more resilient to extreme temperatures. For instance, on a planet free of humans, we can expect the development of organisms capable of surviving in conditions of increased radiation, similar to some bacteria that already demonstrate such adaptations today. Ultimately, new ecosystems may form in bodies of water, creating unique communities of organisms adapted to life in high concentrations of carbon dioxide. This could lead to the emergence of new life forms capable of using carbon dioxide for photosynthesis. For example, scientists are already studying microbes that can convert carbon dioxide into oxygen and carbohydrates, which could form the basis for new ecosystems. On land where cities and factories once stood, dense forests may arise, populated by adapted plant and animal species. Plants like lotuses already exhibit remarkable adaptability to changing conditions, and their descendants may develop the ability to survive in conditions where pollution and extreme climatic conditions become the norm. Animals are likely to evolve to fill the niches left vacant by the disappearance of humans. For example, mammals may return to tree-dwelling lifestyles, as their ancestors did, or adapt to subterranean life, as modern moles do. In ecosystems previously dominated by humans, new predators may emerge to take their place, much like how wolves and bears returned to regions where human hunters once roamed. In the absence of human activity, there may be a significant recovery of biodiversity, with new species developing from existing ones, as has happened after mass extinctions in Earth's history. For instance, after the extinction of the dinosaurs, mammals filled their niches and diversified into a wide range of groups, from small rodents to giant elephants. In the future, there may be organisms with completely unusual forms and functions, such as multicellular organisms capable of symbiotic relationships with fungi to obtain nutrients. These symbiotic relationships could become the primary means of survival in conditions of limited resources. Given the speed at which ecosystems are changing, it is safe to predict that in a few million years, Earth may become home to beings that are completely unlike those that inhabited it in the 21st century. Evolutionary processes, ongoing for millions of years, will determine how organisms will react to new conditions and how they will develop in the changing world. Ultimately, life on Earth will not only survive but also adapt, filling the ecological niches left behind by humanity. For example, in conditions of increased temperature and changing climate, there may be the emergence of life forms capable of surviving in high concentrations of salt, like some modern plants such as saltworts. In such conditions, new ecosystems may form in places where cities once stood, with unique species that will be completely dependent on the new climatic conditions. The Earth, as a planet, is a dynamic system where changes occur constantly and on a large scale. Approximately 3 billion years from now, due to internal activities such as plate tectonics, volcanism, and changes in the chemical composition of the mantle, continents may be completely redistributed. Scientific research shows that during this time, oceans may significantly change, possibly disappearing or forming in new places. There are hypotheses that oceans could become more salty if current tectonic processes continue, which would affect existing ecosystems. On the other hand, solar activity will increase, and ultimately, this will lead to the atmosphere of Earth losing oxygen, making life as we know it impossible. Scientists like Dr. Frederick Hoyle from NASA suggest that in this scenario, life will be forced to adapt to new conditions or even evolve into completely different forms. In billions of years, when the level of carbon dioxide in the atmosphere significantly increases, it will create a greenhouse effect that could lead to the surface temperature of the planet rising to critical levels, comparable to the conditions on Venus. In such conditions, where the temperature could reach over 300 degrees Celsius, any remaining forms of life would likely be concentrated in deep hydrothermal sources, hidden from the harsh surface conditions. Meanwhile, on many parts of Earth, remnants of human civilization will remain, but they will be perceived as artifacts of a distant past, similar to the findings of ancient civilizations like the Maya or Sumerians, whose achievements are still studied by archaeologists. Humanity is just a fleeting moment in the history of the planet, and its influence, although significant, will be just one of many chapters in the book written by Earth. Oceans, once teeming with life and diversity, may become empty, and continents may become vast deserts where the dominant role will belong to bacteria and other microorganisms capable of surviving in extreme conditions. On the horizon of billions of years ahead, when the Sun becomes a red giant, it will engulf the inner planets, including Earth, marking the final chapter in the history of our planet. These changes occur on such vast timescales that human history cannot fit into this cosmic context. Therefore, Earth continues its journey through endless time, remaining an object of study and wonder for future civilizations that may arise in some distant corner of the universe. Currently, the level of carbon dioxide in the atmosphere is over 400 parts per million, which is already affecting the climate conditions on the planet. Our Sun, the star that has been shining for billions of years, is gradually increasing its brightness, and this process will continue in the future. Scientists predict that in approximately 1 billion years, solar radiation will be 25% stronger than it is now. This increase in brightness will lead to a significant rise in temperature on Earth's surface. It is expected that by that time, the temperature on the planet will reach critical levels that will make the existence of complex life forms impossible. In the oceans, which currently cover more than 70% of Earth's surface, the process of evaporation will begin. Research shows that at temperatures above 100 degrees Celsius, water will evaporate so quickly that the oceans could decrease to critical levels within a few million years. This event will change the planet's climate, making it resemble Venus, where the temperature exceeds 400 degrees Celsius and the atmosphere is mainly composed of carbon dioxide. Biodiversity will rapidly decline as ecosystems will not be able to adapt to such rapid changes. All living organisms will retreat to the poles, where conditions will be less extreme. The polar regions, which are currently cold and sparsely populated, will become the last sanctuaries for life. Scientists predict that flora and fauna will go extinct, and only the most resilient species will survive in the conditions of increased temperature and reduced available water. Climate change models show that ecosystems such as tropical forests will completely disappear as the conditions for their existence will become too harsh. Ultimately, if no catastrophic events occur to alter this trajectory, Earth will become a barren planet, where only the remnants of once thriving biosphere will remain. Thus, in several hundred million years, when the Sun's brightness reaches critical levels, vast expanses of land that were once covered with green forests and blooming fields will turn into lifeless deserts. In the distant future, when Earth's internal heat finally runs out, active tectonic plate movements will cease, and the planet will become geologically dead. This will happen billions of years from now, when the temperature in the mantle drops to critical levels and the convection currents responsible for the movement of tectonic plates slow down to a minimum. Currently, the temperature in Earth's mantle is around 1,300 degrees Celsius, but over time, according to geologists' calculations, it will gradually decrease. As a result of this process, continents will stop moving, and the movement of lithospheric plates, which currently creates mountain ranges, volcanoes, and earthquakes, will become zero. Erosion, acting over tens of millions of years, will smooth out the existing relief, and once mighty mountains like the Himalayas or the Alps will become low hills, barely noticeable against the vast plains. Volcanic activity, which now forms new lands and releases carbon dioxide into the atmosphere, will cease, leaving the planet without new mineral and fossil fuel sources. Research shows that in the absence of tectonic activity, the cycle of elements necessary for supporting complex life is disrupted. For example, without volcanic activity, there will be no release of essential life gases such as sulfur dioxide or carbon dioxide. Since these gases play a crucial role in forming the atmosphere and maintaining the climate, their absence will lead to a sharp change in surface conditions. Ultimately, the planet will become a place where life cannot exist, and oceans, once full of energy and diversity, will turn into salty puddles, while the atmosphere will become thin and lifeless. The process of decomposition of existing life forms will continue, but without new sources of energy and nutrients, it will become irreversible. Thus, billions of years from now, Earth will transform into a cold, desolate world where the remnants of once bustling life will be submerged in eternal silence. At this time, geological processes that have shaped the planet throughout its history will be completely stopped, and Earth will become as dead as the moon, without any signs of activity or changes. In 5 to 7 billion years, the Sun will enter its final stage of life, transforming into a red giant. At this point, it will begin to expand, increasing its size until it reaches a radius greater than the orbit of Earth. According to astronomers, the diameter of the Sun at this time could be up to 1,400,000 kilometers. The process of expansion will be accompanied by intense energy release, leading to a sharp increase in temperature on the planet. As a result of this heat, the oceans of Earth will start to evaporate, forming clouds of water vapor that will then be carried into the upper layers of the atmosphere. Each year, the oceans will become smaller and smaller, until they eventually disappear completely. The atmosphere of Earth will also not withstand the influence of the scorching light. Oxygen and nitrogen will be destroyed by ultraviolet radiation, while carbon dioxide, which currently makes up a small part of the atmosphere, will rapidly increase, creating a greenhouse effect. This will result in the planet's surface resembling hell. Temperatures could reach over 1,000 degrees Celsius. When the Sun becomes a red giant, its light will illuminate the scorched deserts left behind from the once thriving planet, and its surface will be covered with devastated landscapes and debris. At this moment, the Sun will occupy a large part of the sky, appearing as a massive red disk that will fill the horizon, shimmering in various shades. Earth, as a planet, will exist only as a hot, lifeless wasteland, devoid of water, life, and atmosphere. Against this grand finale of our planet, something extraordinary will happen. The Sun will begin to shed its outer layers, forming a planetary nebula that will shine in the cosmos, while the core of the star, compressed by gravity, will become a white dwarf. This white dwarf, retaining only a small fraction of its original mass, will slowly fade over billions of years until it becomes a cold, dead object wandering through the cosmos. In the end, the entire solar system, including the planets, will fade away, leaving behind only the echo of past life. Geological heritage of the Earth represents a vast chronicle inscribed in the layers of rock, where each page preserves information about billions of years of planetary evolution. These layers are formed through various geological processes such as volcanism, erosion, sedimentation, and plate tectonics. For instance, when a volcano erupts, lava flows, ash and gas accumulate and solidify, forming new rock types. These sedimentary layers can contain traces of organic life, such as fossils, which provide insights into the biological species that inhabited Earth during different periods. Geologists use stratigraphy to analyze the sequence of layers, allowing them to reconstruct historical events like mass extinctions or climate changes that occurred millions of years ago. For example, studying layers formed after a meteorite impact can help understand how this catastrophic event affected life on the planet. Each layer of rock can be seen as a page in a book, recording significant events such as temperature changes, sea level fluctuations, and atmospheric composition over time. Dating these layers enables scientists to determine the age of formations, and with radiometric methods, it is possible to determine that some of them are over 4 billion years old. In this context, geological heritage becomes not only a repository of information, but also a tool that helps us understand how Earth has changed and adapted to various conditions. In different parts of the planet, traces of ancient oceans, deserts, or ice sheets can be found, which once occupied vast territories. For example, salt crystals found in rocks can indicate that an ocean once existed in that region and later dried up. Thus, Geological heritage of the Earth is an invaluable resource that allows us not only to study the past, but also to predict the future by examining how the planet reacted to changes in its environment. These processes and their consequences over billions of years continue to shape the landscape, and each new layer adds new data to the overall picture. Complex interactions between the Earth's crust, atmosphere, and biosphere over time create unique conditions for life, making the study of geological heritage particularly relevant in light of contemporary climate changes. For example, analyzing glacial deposits can help understand how climate changed in the past and what consequences it had for ecosystems. The glacial period that occurred around 100,000 years ago left traces in the form of glacial deposits and landforms that can still be observed today. As a result, studying geological heritage allows us not only to examine ancient processes, but also to gain insights into the current and future challenges that the planet faces. Each layer of rock is not just minerals and fossils. It is evidence of how Earth has survived and adapted, and this evidence is available for research and analysis. The study of ancient catastrophes is a complex and multifaceted process that requires the use of various methods and technologies. One of the fundamental techniques is isotope analysis. Isotope analysis allows scientists to determine the chemical composition of ancient samples, enabling them to understand climate and ecosystem changes over different geological epochs. For example, analyzing carbon isotopes in corals and sedimentary rock layers helps reconstruct atmospheric levels of carbon dioxide, which in turn indicates events related to global warming or glaciation. Comparative analysis of oxygen isotopes in ice cores allows scientists to establish temperature fluctuations that occurred on Earth over the past several million years. Paleontological data also play a crucial role in understanding ancient catastrophes. For instance, fossilized flora and fauna remains help reconstruct the evolution of living organisms and their responses to environmental changes. Scientists like Dr. Peter Dodson, who studied fossils in the larger formation, discovered evidence of a mass extinction of dinosaurs that occurred around 65 million years ago, possibly linked to an asteroid impact. These fossils show how ecosystems recovered and adapted after catastrophic events such as volcanic eruptions or sea level changes. Geophysical research, including seismic tomography, also plays a significant role in studying ancient catastrophes. This technique allows scientists to look into the Earth's interior and examine structures that may indicate tectonic activities. For example, in 2000, researchers using these methods discovered previously unknown underwater canyons created by ancient earthquakes. The discovery of these canyons provided new data on the frequency and intensity of seismic events in the region. Geophysical methods help not only in studying the past, but also in predicting future catastrophes based on historical data on earthquakes and volcanic activity. Modern technologies, such as radiocarbon dating, enable precise determination of sample ages, significantly enhancing the possibility of chronostratigraphic analysis. For example, in 2015, a group of scientists from the Massachusetts Institute of Technology used radiocarbon dating to determine the age of fossils found in Brazil and established that they date back to around 100 million years ago. This discovery expanded knowledge about the biodiversity of that era and the conditions in which organisms evolved. Additionally, remote sensing technologies allow for the collection of data over large areas, aiding in the study of geological processes and landscape changes. For instance, satellite imagery enables scientists to monitor changes in glaciers and their impact on sea levels. The processing of data using artificial intelligence and machine learning is becoming increasingly popular in research as it allows for the processing of vast amounts of information and the identification of patterns that would be difficult to notice manually. These methods significantly accelerate the analysis process, allowing scientists to focus on interpreting data rather than collecting it. Thus, the combination of various methods, from isotope analysis to geophysical research, creates a comprehensive approach to studying ancient catastrophes, enabling scientists to reconstruct the events that occurred millions and billions of years ago and make inferences about the possible future of the planet. For example, research results show that during the Permian-Triassic extinction event, which occurred around 250 million years ago, up to 90% of all species disappeared, highlighting the importance of understanding catastrophic events for preserving modern biodiversity. The study of geological catastrophes provides invaluable insights into how the planet has responded to extreme changes, allowing scientists to extrapolate these findings to contemporary processes. For instance, the analysis of impact craters, such as the Chicxulub crater in Mexico, confirms that around 65 million years ago, the fall of an asteroid led to the mass extinction of dinosaurs and most other species on Earth. This event, caused by catastrophic impact, demonstrates how sudden and powerful natural forces can alter ecosystems. Scientists like Dr. Richard Knott from the University of Cambridge study samples of sedimentary rocks to understand how climate changes and tectonic processes have influenced life on the planet. These studies help predict how current climate changes might lead to similar catastrophes in the future. For example, in recent decades, there has been an increase in the frequency of extreme weather events such as hurricanes and floods, which can be predicted by studying ancient climate data. This underscores that knowledge of how Earth has coped with changes in the past can help us adapt to today's challenges. The study of geological catastrophes also illustrates how humanity must accept its place on the planet and recognize that we do not control all aspects of the environment. For example, analysis of data collected during research in the Pacific region has shown that powerful earthquakes resulting from the movement of tectonic plates can trigger tsunamis, highlighting the importance of preparedness for potential catastrophes. For instance, in 2011, Japan experienced one of the most devastating earthquakes in history, caused by the collision of the Pacific and Eurasian plates, which led to a tsunami and a nuclear disaster at Fukushima. These events serve as a reminder that geological processes continue to influence human life and ecosystems. The use of historical data helps governments and organizations develop strategies to mitigate risks associated with natural disasters. For example, in the Netherlands, active research is being conducted to manage flood risks based on data from past floods, enabling the creation of effective protective systems. Modern technologies such as satellite imagery and modeling allow scientists to more accurately predict the consequences of natural disasters and their impact on populations. The application of these methods in conjunction with historical data creates a powerful tool for planning and adaptation. Therefore, the study of geological catastrophes not only helps us understand how the Earth functions, but also equips us with the knowledge necessary for survival in a world where natural forces can be unpredictable and destructive. Scientific research continues to confirm that understanding Earth's history is the key to the survival of future generations. For example, data collected from ice core samples shows that sea levels have risen by 25 centimeters over the last 100 years, threatening coastal communities. Geological catastrophes, such as volcanic eruptions, earthquakes, and asteroid impacts, not only shape the landscape of Earth, but also influence our philosophical understanding of life. The realization that our planet is subject to destructive natural forces leads us to reflect on the fragility of human existence. For instance, around 65 million years ago, a catastrophic asteroid impact led to the mass extinction of dinosaurs, paving the way for mammals to become the dominant species on Earth. This event illustrates how random the evolutionary process can be. Some species disappear, while others survive and thrive. Scientific research shows that such catastrophes occur with a certain periodicity, and Earth's geological history records at least 5 major mass extinctions, each altering the course of evolution. Understanding this fact underscores that the development of life does not follow a linear trajectory, but rather resembles a chaotic movement influenced by external factors beyond our control. In this context, the philosophical interpretation of catastrophes becomes significant. They remind us that progress is often intertwined with destruction. For example, in the 20th century, scientists like Paul F. Hawking studied the impact of climate changes caused by volcanic activity on the biosphere. Their research shows that even short-term climate changes can have long-term consequences for ecosystems. Consequently, we begin to realize that human existence on Earth is but a fleeting moment in the context of geological time. Our dependence on the stability of ecosystems and climate makes us vulnerable to natural catastrophes. This leads to contemplation about how humanity should adapt to the inevitable changes brought about by such catastrophes. For instance, contemporary scientists like Christopher Faulkner study how ancient civilizations, such as the Maya or the Incas, coped with climate changes and how their culture and society evolved in response to these challenges. Understanding these processes helps us realize that we are not the sole masters of Earth. Our existence depends on our interaction with the surrounding environment. This awareness can change our perception of progress, compelling us to view it as part of a broader ecosystem in which we are intricately connected to nature. Each step of human progress towards technological advancement can be nullified in an instant if we do not consider the influence of planetary forces. Massive carbon dioxide emissions, driven by human activity, can lead to global catastrophes similar to those that occurred in the past. For example, the Permian Triassic extinction event, which saw the loss of around 97% of all species, demonstrates how quickly ecosystems can change under catastrophic influences. This awareness raises important questions about our role in the ecosystem and how we can preserve our planet for future generations. Scientific data shows that the Earth's temperature has risen by 1 degree Celsius since the beginning of the Industrial Revolution. And without significant efforts to reduce emissions, we may face consequences comparable to the largest geological catastrophes of the past. Each of these events forces us to consider our role in this world and the fact that, despite our achievements, we remain part of a complex and unpredictable system where every action can have consequences. In this context, the philosophy of catastrophes becomes not just a study of the past, but a crucial tool for shaping our future. Catastrophes throughout Earth's history, from powerful volcanic eruptions to devastating asteroid impacts, played a paradoxical role in the evolution of life. These events, causing irreparable damage, simultaneously became catalysts for change and innovation. For instance, around 66 million years ago, at the end of the Cretaceous period, one of the most famous mass extinctions occurred, when around 75% of all species on the planet disappeared. This event, caused by a collision with an asteroid approximately 10 kilometers in diameter, opened up new ecological niches. With the disappearance of dinosaurs, which dominated the land, mammals had the opportunity to occupy the freed territories, leading to the emergence of groups such as primates and ultimately to humans. While previously mammals were in the shadow of giant reptiles, the catastrophe created an opportunity for their rapid diversification and adaptation. Similarly, as a result of volcanic activity, such as the eruption of the Toba volcano around 70,000 years ago, a global volcanic winter occurred, leading to a significant reduction in the human population. However, this catastrophe likely contributed to the development of new cultural practices and technologies, as the surviving groups adapted to the changed conditions. Every end, whether it be the extinction of a species or an entire ecosystem, creates space for a new beginning. In this context, one can remember events like the extinction of trilobites, which paved the way for the flourishing of other marine organisms such as fish and mollusks. Each layer of sedimentary rocks on Earth contains evidence of catastrophes that led to the creation of new ecosystems and species. These cycles of destruction and restoration highlight not only the fragility of life, but also its remarkable ability to adapt and renew itself. In this process, Earth itself acts as a living organism that is constantly transforming, where each generation of organisms, coming and going, leaves its mark on the geological history. These transformations occur on scales that may seem incomprehensible to us, but they are part of the continuous cycle of life on the planet. Each new landscape formation or appearance of a new species is a step towards the creation of more complex ecosystems. Looking back over billions of years of geological history, one can say that this process of transforming the planet resembles an endless cycle, where each end becomes the beginning of something new. As you lie down to sleep in the evening, reflect on the magnificent history of our home in the universe, where the images of ancient catastrophes and rebirths can merge with your own dreams, creating new, wondrous worlds.